ಈಗ ಆಯ್ತು. ಈಗ ನಾ ಮಾತಾಡೋದು ಕೇಳಿಸ್ತಾ ಇದೆಯಾ ನೋಡ್ಲಿಕ್ಕೆ ಹೇಳಿ ಅವರಿಗೆ. ಹಲೋ ಹಲೋ, am I audible? ಹಲೋ, am I audible? ನಾ ಮಾತಾಡೋದು ಕೇಳಿಸ್ತಾ ಇದೆ ಕೇಳಿ ಅವರಿಗೆ. ಕೇಳಿಸ್ತಾ ಇದೆಯಲ್ಲ? ಸರಿ, ಅಷ್ಟೇ ಬೇಕಾಗಿತ್ತು.
Hello. Please check it. Check it. Check it. ಬರ್ತಲ್ಲ ಕ್ಲಿಯರ್ ಆಗುತ್ತಲ್ಲ ಹಾ ಸರ್ ಅನ್ಮ್ಯೂಟ್ ಮಾಡ್ಲಿ ಮ್ಯೂಟ್ ಮಾಡಿ
Hello. Yes.
Hello, good morning. ನಿಮಗೆ ಕೇಳಿದ್ರು
Good morning, everyone. We are going to start this session in another 10 minutes. Within 10 minutes. Nothing is impossible for those who have these 6 virtues: knowledge, logic, science, memory, readiness, and ability to function. A very good morning to one and all gathered here. I'm Kiran Gargi, Assistant Professor, Department of Zoology, PC Jabin Science College, Hubballi. I heartily welcome you all to this National Conference on Statistical Modeling and Inference organized by Department of Statistics, School of Computational Sciences, and IQSC initiative. Now, I request our beloved principal, Dr. L.D. Horkeri, to welcome the gathering. Over to you, sir. I request our beloved principal, Dr. L.D. Horkeri, to welcome the gathering.
Wait, madam, wait.
joined this virtual program. At the same time, it is very important to welcome wholeheartedly all the delegates who have joined this and who are going to present their papers orally and virtually. So I extend a warm welcome to you all delegates, friends. Welcome you all. I extend a warm and sincere welcome our student friends who have joined this workshop. So we are having a overwhelming response to the national level conference. Already we have received more than 10 research papers going to be presented in this national level workshop. So once again, I extend a wholehearted welcome to all present over here. Thank you. Thanks a lot.
Thank you, sir. Now I request Dr. C.M. Mutt, Head of School of Computational Sciences, PC Jabin Science College, Hubballi, to speak about the conference.
Good morning, all. Honorable Board Member of KLE Societies, Sri S.I. Murali sir, our beloved Principal, Dr. L.D. Varkar sir, invited speakers, Dr. Parameshwar Pandit, Dr. S.P. Murali, Dr. P.G. Dikshit, and all advisory committee members, organizing committee members, research scholars, faculty members, and my dear students. Department of Statistics, KLE's Society's PC Jabin Science College, Hubballi was established in the year 1959. Initially, the department began with major and minor courses here. Since 1990, 3 subjects of equal importance was introduced for a BSc. CBCS was introduced in the year 1920, and NEP 2020 was introduced from this academic year 21-22. Department of Statistics is committed to excellence in teaching and equipping students to become a practicing statisticians. Department provides platform to the students to analyze the real life data, drawing conclusions and supporting conclusions by explaining the reasoning behind them. The School of Computational Science, Department of Statistics organized national level conference on statistical modeling and inference. The main goal of the conference is to bring to undergraduate, postgraduate students at one platform along with research scholars. The main theme of the seminar is statistical modeling, statistical inference, statistical analysis in social science research, biostatistics, statistical quality control, data analytics, reliability analysis, and in the mathematics also some subjects is included here. That is the differential geometry, topology, and dynamic systems. The conference is to encourage young budding statisticians to become researchers of statistics, practicing statisticians, and so on. Conference on statistical practice brings together hundreds of statistical practitioners, including data analytics, researchers, scientists, engaged in the applications of statistics on daily basis. In this conference, faculty, research scholars, UG and PG students are encouraged to present their original unpublished research work, and reviewed papers will be published in ISBN journal. Now, in this conference, there are 10 research papers are issued and they are presenting today in the conference. In the conference, there are more than 122 participants are taken the active part in the conference here. Out of that, more than 50% of the students of the faculty or the research scholars joined from the outside the state, especially Maharashtra, Andhra Pradesh, and Telangana. And at this stage, really for conducting this the national level conference, they helped a lot in the advisory committee, especially Dr. Parameshwar Pandit, Sharda Bhatt, Sujata Ingansetti, B.S. Biradar, Ainapur, Pushpanjali Madam, Dr. V.V. Gute, P.G. Dikshit, and Mk Patil, from the Maharashtra, and Raghunath Reddy, Dr. S.B. Jowli, and many of them to help in this conducting the organization here. So without the help of these advisory committee members, I can't taken into the conference, such the big conference initially now here. I am also very happy to accepting the advice from the Sharda Bhatt madam also here. So for this conference, the many of them taken a very active part here. Now I am wishing to all the participants to participation in this national conference. Thank you one and all.
Thank you, sir. It's a privilege to have Sri Shankaranna Munvalli ji, Director, Board of Management, Keli Society, Belgavi, with us today. So I request Sri Shankaranna Munvalli ji to address the gathering. Thank you, sir. My deep sense of gratitude to you, sir, for your valuable words and for spending your precious time with us. Thank you. Now, it's the time to resume session 1. I feel privileged to introduce Chairperson of the session, Dr. Srimati Sharada Bhatt, Professor and Chairman, Department of Statistics, Karnataka University, Dharwad. She has completed MSc PhD in Statistics and her area of research is Non-Parametric Inference and Bayesian Inference. Madam has published 39 publications, including research and general articles on statistics. She has actively participated in 49 conferences and seminars and has membership of many professional organizations. She has served for many associations in KUD. With this brief introduction, I wholeheartedly welcome Srimati Sharada Bhatt. Welcome you, Madam. And I also welcome keynote speaker of this session, Dr. Parmeshwar V. Pandit, Professor and Chairman, Department of Statistics, Bangalore University, Bengaluru. I welcome you, sir. Now, I request Mr. Venkateshwar Rao, Assistant Professor, Department of Statistics, to introduce the keynote speaker of this session. Over to you, sir.
Dignitaries, research scholars, faculty members, and my dear students, a very good morning to one and all. Myself, Venkateshwar Rao, Assistant Professor, Department of Statistics, PC Jabin Science College, Hubballi. It's a great pleasure for me to introduce and welcome our speaker, Dr. Parmeshwar V. Pandit sir, who is going to talk to us about statistical inference for stress, strength, reliability for some specific distribution. Sir, presently working as a chairman, professor, Department of Statistics, Bangalore University, Bengaluru. Sir, presently holding key role position in administration, in that Director, IQAC, Bangalore University, Director, IT Center, Bangalore University, and other roles like member, expert committee, Directorate of Economics and Statistics, Government of Karnataka, member, technical and administrative committee, Bangalore University. Sir has more than 32 years of teaching experience and more than 28 years of experience in research. Sir was guided 9 PhD scholars successfully. Presently, Sir guiding 2 PhD scholars. Sir worked as a reviewer or editorial for various national, international journals and publications. Sir referred publications are 92, in that national level 35, international level 52, others 2 are submitted and 3. Sir was completed 3 minor and 1 major UGC projects. Sir was attended more than 58 conferences and presented papers. Sir's research interests are non-parametric inference, distribution-free robustness of sequential probability ratio tests, inference in reliability, parametric inference, goodness of fit, tests for normality. Sir was life member for more than 6 national, international professional bodies. Sir worked as a subject expert in BOA for many universities. Sir worked as an external member BOE of many universities in and outside of Karnataka. Member BOS of many universities in and outside of Karnataka. Presently holding the position as a chairman BOS for 4 universities. Sir has undertaken 1 collaborative work with Dr. Dielectric of Kolhapur University. to Dr. Sri Sharda V. Bhatt, ma'am. Please, ma'am. Thank you.
Namaste, everyone. Good morning. So, first of all, I thank the organizers for inviting me to this national level conference on statistical modeling and inference. Now it is time for our keynote speaker to address us. So I invite Professor P.V. Pandit for his keynote address. This session will go for next 45 minutes. Professor Pandit addressing us on statistical inference on stress strength reliability for some specific distribution. So I welcome you, Professor Pandit. Namaste, please.
Sir, your voice is not audible. No, sir. Hello. No, sir. Not audible, sir. Now, okay, sir. Now, okay.
Please allow me to share the screen.
Okay, sir. Now you can share. Hello, sir. Voice is not audible, sir.
Hello.
Hello. Okay, sir. Now, okay.
Am I audible?
Yes, sir.
Okay. So the title of my talk is Statistical Inference on Stress Strength Reliability for some specific distributions. I'm considering specifically here some four distributions, namely the inverse chain, generalized Pareto, bivariate generalized Rayleigh, and transported exponential inverse Rayleigh distribution. And I'm concentrating on the first three, and if time permits, I will just address the last distribution, that is transported exponentiated inverse Rayleigh distribution. Okay, so my plan of the talk. Okay.
Sir, not audible, sir. Hello. Hello, sir. Hello, sir. Hello. Sir, it is not audible. Hello, sir. No, sir. Not audible. No, sir. Hello.
Hello, just a minute.
Now it is correct, sir.
Yeah.
Now it is audible.
Okay. So my plan of the talk is the following. So I'm just giving you the introduction along with the literature survey. In each case, I'm giving literature survey separately. First, I'm considering inverse chain distribution, estimating the reliability when you have a single component system, and also multi-component system, in particular parallel and series systems. And we have considered the estimation of this reliability using maximum likelihood method when the sample is simple random sample or ranked sampling. And also we have considered base estimation of the reliability in each of the cases when you have a single component system or parallel system or series system under stress-strength setup. Okay, and in particular for base estimation, an approximation has been considered, that is due to Lindley. And next, I'm considering the generalized Pareto distribution as a distribution. For that also, my problem is to estimate the stress-strength reliability and using maximum likelihood method as well as base method. The next, I'm considering bivariate generalized Rayleigh distribution, and I'm estimating the reliability. And here it's a bivariate generalized Rayleigh. I'm converting this to the univariate setup, and the procedure follows as the above. So now, finally, I'm just introducing transmuted family of distributions, and a particular transmuted distribution I'm just trying to address, and then I'm concluding with some remarks and conclusions.
Sir, it's not audible, sir. Sir, not audible. Hello? Yeah, yes, now it's audible. Continue, sir.
So the problem of estimation is to estimate R, that is probability of y less than x, when x is the strength and y is the stress, and both variables follow inverse chain distribution. They are not IID, but they are independent and not identically distributed. So this estimation of that is carried out using maximum likelihood and Bayesian methods, as I told you, and a simulation study is conducted to evaluate the performance of the estimators using mean square error criteria. So some literature exists are. See, in 1971, Ennis and Geezer, Tong, Govindarajulu, Woodworth and Kelly considered the problem of estimating reliability in a system setup when x and y follow exponential, variable, Pareto, gamma, etc. So in 2008, Recap estimated the reliability of the model for a 3-parameter generalized exponential distribution, and 2013, Solomon et al. Considered Bayesian estimation of R when x and y are independent modified variable distribution. So in the recent years, the researchers have shown interest in estimating stress-strength reliability using ranked sampling scheme. So in 2010, Mutek et al. Estimated the reliability when x and y follow exponential distribution. Hussain considered this problem based on for inverted exponential distribution based on RSS and simple random sampling. Hassan et al. Studied the estimation of R when x and y are independently distributed per value random variables based on ranked sampling. So these are not exhaustive. Some of the references, some of the earlier work I have considered. So first, let me give you the inversion distribution, the distribution function and density. So the distribution function of the inversion distribution is the following. It has two parameters. One is the scale and the shape, gamma and beta. And this is the distribution function of this distribution. And f of x, this is the density function of inversion distribution. So the inversion distribution has a hazard function as the following: hx, this, and this is the useful model for lifetime of units which have early failures. And we can see the graph function. You can see that there is a the curve looks like some kind of a chi-square distribution curve, and of course, it for different values of scale and shape parameter, you have these. This. So it's something like inverse bathtub curve, not exactly. So now, under this system setup, the reliability of the component is obtained, assuming that x has inversion distribution with gamma and beta, and y also has inversion distribution, but with a different scale parameter delta and beta. And the system reliability is given by is derived as gamma by delta plus gamma. And here you can see that if the shape parameters are same, then we get it to the reliability depends on only the scale parameter. So now, under simple random sample setup, we obtain maximum likelihood estimation. So in that, suppose you have two random samples from inversion distribution with the common shape parameter and different scale parameter, the likelihood function is given in 2, and you have the log likelihood in 3. Then to get maximum likelihood estimation, we get the likelihood equations, and we get MLE of gamma and delta as function of beta as the following, and in 7 and 8 it is given. Gamma hat and delta hat are the functions of beta, which is unknown, and we have to estimate beta. However, beta, the expression for beta is not possible. Hence, beta hat is the solution of a nonlinear equation of the form h beta equal to beta, so where h beta is given by the equation 9. So to solve for beta, we use a numerical technique. Particularly here we have used Newton-Raphson method. Any other numerical technique also can be used. And we get the, once if you get beta hat, we can plug in beta hat in the expression for gamma hat and delta hat, and we get the expression, estimate for reliability. So now, the maximum likelihood estimation of R under ranked sampling scheme. So first, let me briefly give the basic ranked sampling scheme. In ranked sampling, what we do is a simple random sample of size m is drawn from the population, and m units are ranked with respect to the variable of interest, say x, by judgment without actual measurements. So then the unit with rank 1 is identified and taken for the measurement of x. So the remaining units of the sample are discarded. Next, another simple random sample of size m is drawn, and the units of the sample are ranked by judgment, and unit with rank 2 is taken for the measurement of x. So we have two observations, and similarly, we continue this process is continued until a simple random sample of size m is taken and ranked. Then the unit with rank m is taken for measurement of x. this whole process is referred to as a cycle, and the cycle then repeats k times and yields a Rankin-Search sample of size capital N is equal to m into k. So suppose I have at xi mx I equal to 1 to mx, j equal to 1 to rx be a Rankin-Search samples with sample size nx is equal to mx into rx, where mx is the set size and rx is the number of cycles drawn from inverse chain distribution with parameters gamma and beta. Similarly, the y k my be a Rankin-Search sample with the sample size ny equal to my ry from inverse chain distribution with the parameters delta and beta respectively. So for convenience, we denote xi mxj and yk by xij and ykj. So now the PDF of this xij and ykj are given in equations 10 and 11. And the log likelihood function of gamma delta beta given the sample is the following, given in 13. And the likelihood equations are this 14, 15, and 16 to estimate gamma, delta, and beta. I mean, if we solve these equations, we get the expression for delta, beta, gamma, delta, and beta. And once we get the values for the gamma hat, delta hat, and beta hat, the MLEs of R is obtained using invariance property, and it is given like this. So similar procedure is adopted in all the further cases. And next I consider the base estimation of R. So the base estimators are obtained for stress-strength reliability of R, assuming that all the parameters gamma, delta, beta are unknown and independent random variables with gamma priors, say, Ci and delta I. Okay, so this gamma is the conjugate prior for gamma, delta, and beta, and the PDF we considered is this, and the joint prior for gamma, delta, beta is the product of the densities with respect to gamma, delta, beta, and we have a hyperparameters C1, C2, C3, and D1, D2, D3. So substituting LS and gamma, G of gamma, delta, beta, the corresponding joint posterior density of gamma, delta, beta is given by this. Okay. Here we can see that this pi gamma, delta, beta is the ratio of two integrals, the ratio of two quantities. The denominator is a it's an integral, and numerator is something. And if you go for finding the base estimator, we have to get the expected value of posterior mean. We have to find out, because we are considering a square root loss function as the loss function. So we get the expected mean is the ratio of two integrals. So for that we use an approximation, that is the Lindais approximation. So that I am skipping a Lindais approximation, and we obtain the R hat B, that's the base estimator of R, that is R hat B. So this we are evaluating. As I already told, it is very difficult to solve equation. I mean, it is very difficult to evaluate this integral, that is 17 analytically. So we go for approximation, that is Lindais approximation. So there are other approximation techniques also available in the literature, like Kairani and Chadani, and also efficiency techniques also can be used. But however, we have used this Lindais approximation as an approximation method to evaluate this. Okay, I am not going to explain this Lindais approximation. For Lindais approximation, we require maximum likelihood estimators, because this involves maximum likelihood estimators, and I'm skipping this details. So RB hat comes in terms of this, and here you can see that it involves U1, A1, U2, UIs and AIs, and also sigma ij's, B, A, and C. These quantities are evaluated. So, not to compare these estimators, we have conducted a simulation study based on 1 lakh random samples of different sizes, of course. For simple random sampling N and M, and for random rank sampling MX, MY, RX, RY were considered for this, and the values of gamma, delta, beta used for comparison are this. So I am considering only 3 different sets, that is sets of values for gamma, delta, beta for illustration. Of course, we have evaluated for a large number of sets, and we obtain almost similar results. So for base estimators, you have to consider the hyperparameters also. So C1, C2, C3, D1, D2, D3 are to be taken. That is, we call it as prior 1 if we have this set 7, 4, 1, 4, 3, 1, and prior 2. 2 priors we have considered, and we have evaluated the mean square errors for these. So you can see that if you see the mean square errors of the different estimators, the maximum MLEs under SRS, under RSS, and the base estimator with this prior 1, and we can see that base estimator is of course better marginally, but however we can compare it with rank sampling scheme, and not that there's not much difference between the MLEs obtained using rank sampling and base estimators. So in general, what we can say is base estimator with this prior is uniformly better with reference to what I have considered here. I cannot generalize it, and similar results have been obtained with the different prior and different parameter values also. So this is the remarks with reference to the estimation of reliability under stress level for a single component system. The problem at test is the estimation of stress reliability when XY follow inverse chain distribution. MLEs of R is derived both under simple random sampling and rank rate sampling schemes. Base estimators are also obtained, and what we observe there is MLE obtained RSS scheme is better than that under SRS. As compared to maximum likelihood estimators under SRS and RSS, the performance of base estimators are better uniform. Next, I'm considering the multi-component system and stress and strength variable follow again inverse chain distribution, and here stress strength reliability for a multi-component system consisting of k identical components is considered. The k components of the system with random strengths x1, x2, so on xk are subject to one of the R random stresses, k xk plus 1, xk plus 2, so on xk plus R, when the system is either parallel or series with the assumption that strengths and stresses follow inverse chain distribution. Some of the related works in the literature are Kunchur and Munoli 1993 derived stress strength reliability for multi-component model based on exponential distribution for parallel system. Hangal 1996 considered problem of estimating estimation of probability of x3 greater than maximum of x1, x2. It is a single component system, but the stresses are two stresses. When x1, x2 follow bivariate exponential distribution and x3 follow independent exponential distribution. So there are many papers written by Hangal. I just consider I just mentioned here, until 1998 and until 2003, it has been considered for a series system, parallel system, series and parallel system, or when Pareto variable gamma distributions are considered. So what we can observe is in all these papers, estimation of system reliability is considered by taking maximum of 2 stresses. So here, the problem of estimation of reliability with arbitrary number of stresses was first addressed by Pandit and Kant in 2013, when strength and stress variables follow independent exponential distribution. So what is the formulation of the model? Statistical reliability for a multi-component system consisting of k identical components, the k components of the system with random stresses x1, x2, xk are subject to one of the r random stresses. This here estimation of RP, that is the reliability of a parallel system under stress and setup, and RS are studied when strengths are subject to the one of the R stresses, assuming that both follow 2 parameters, inversion and distribution. The estimation of system reliability is based on, again, maximum likelihood and base. Okay, some of the practical situations where one can think of for a multi-component system is the following. Consider a system of identical generator sets synchronizing with and running in parallel with the supply utility grid. Each generator will be having independent strengths such as the voltage magnitude, the frequency of the voltages, and pulse angles between voltages with independent stresses such as power failures, short circuit currents, earth fault currents, voltage, and frequency transients. Such systems can be considered as a multi-component system with multiple stresses. Another example, in an optical communication system, an optical fiber with independent strength, namely enormous potential bandwidth, sample size, small size, and weight, electrical isolation, immunity to interference, and cross talk, signal security, low transmission loss, potential low cost, etc., is operating under independent stresses such as material absorption, linear scattering losses, filter band losses, dispersion, and polarization. So these are some 2 practical examples. The inversion distribution, which I have introduced by Srivastava and Srivastava 2014, is already stated. The reliability of series system RS is given in 1, then RP is given in 2, and maximum likelihood estimators are obtained. That is the likelihood for log likelihood is given by this log L. Then if you differentiate it, you get the log likelihood equations 3, 4, and 5. If you solve this, you get gamma hat and delta hat. These are the functions of beta. Again, you have to resolve to estimate beta, which is the solution of a nonlinear equation h beta equal to beta. And again, some iterative techniques has to be employed to get beta, and we get the MLEs for RP, that is RP hat, and MLE for RS, that is RS hat, as below. So next we consider base estimation. Base estimation is again here also, since it is inversion, the gamma one can use, and we use Lindler's approximation and obtain the base estimators for RP as RP hat B, and there's a rotational error, and RS hat B, that is based to say that it is a base estimate. So again, simulation study is conducted, and mean squared errors are obtained, and here we can see that in some of the cases, when sample sizes are small, just a minute. For all different sample sizes 5 to 50, we can see that base estimator is uniformly better. However, as compared to MLE. Okay, so here you can see the simulation study shows that base estimators perform better than maximum likelihood estimators for the considered trials. Okay, next I consider S out of K systems under such a setup. That is for generalized Pareto distribution. The idea of S out of K system reliability in Statistical model was first developed by Bhattacharya and Johnson in 1974. The S out of K system reliability can be described as follows. The system having K components with their strength x1, x2, so on, xk, being independently and identically distributed random variables, and each component is experiencing a random stress y. So a system is said to be S out of K system in a stress-strength environment if the system works if at least S component strength exceeds the stress. So this type of systems can be seen both in industrial and military applications. For example, in an electrical power station containing 8 generating units, which produce the electricity only if at least 6 units are working. The demand for the electricity of a district is fulfilled only if S out of K windrows are operating at all times. So for extensive review of this S out of K system, one can refer to Cohen Zhu and 2013. So estimation of multi-component system reliability is considered for different distributions by different authors like Rao and Kantam, series of papers by Rao et al. Recently means since 2015, Kyrgyzstan and other consider the estimation of multi-component system reliability using both classical and Bayesian approach when underlying distribution is variable. So now the multi-component system reliability for S out of K system and with one stress. So you have random variables y, x1 to xk be independent and gy be the cumulative distribution function of y and fx be the cumulative distribution function of x1 to xk, because x1, x2, so on, xk are identically distributed. So the reliability in a multi-component system model for a sort of K system developed by Bhattacharya and Johnson is given by 1 here, RSK. I denote this reliability as RSK. So this is the probability that at least S of x1 to xk exceed y. So this is given by 1. So the system with K components functions if S or more components simultaneously operate. So now the system is subject to a stress y, which is a random variable with distribution function g. The strengths of the components, that is the minimum stressors to cause failure, are independently and identically distributed random variables with distribution function f. So then the reliability of the system is given in 1. This. So what is now we are estimating the reliability under system setup of a sort of K system. When the strengths and stresses are generalized Pareto distribution, which has the following density function fx and distribution function fx. Again, here we have 2 parameters, lambda and alpha, and lambda is the scale parameter and alpha is the shape parameter. So if we, in our case, multi-component system reliability, when x follow this generalized Pareto with alpha 1 and lambda, and y follows generalized Pareto with alpha 2 and lambda, x and y are independently distributed, are considered using equation 1, which is given by RSK is equal to this 2. This is the expression. And then MLEs are obtained. To get the MLEs, we have the likelihood function we have come, the likelihood equations are written, and alpha 1 hat and alpha 2 hat are, we have the closed expressions for that, but it depends on the lambda hat, which we cannot get a closed form expression, and we have to get lambda hat, we need to solve equation h lambda equal to lambda, that is a nonlinear equation, and we use numerical techniques to solve for it. So then after getting that, we get the MLE of RSK. Similarly, we have considered MLE of RSK under aggregate sampling scheme, which we have considered. So there are variations of many variants of aggregate sampling scheme, but the basic aggregate sampling scheme we have considered, and we get the MLEs on the similar lines. Okay, next, again, the same technique we have used to get the place estimators of RSK. That is, again, to evaluate the posterior mean and the square error loss function, we get the posterior mean as the ratio of two integrals. So, it doesn't yield any closed form expression. The solution doesn't yield any closed form expression. Hence, we resort to Lindley's approximation method. And again, simulation study is conducted with two different priors, and of course, this and the performance in terms of MSCs are evaluated, and from MSC again, RSS is better as compared to, MLEs obtained under regular sampling scheme is better as compared to SRS. However, base estimators are better for considered priors. Okay, so next we consider bivariate distribution setup. How much time do I have? How much time do I have? Professor Shadabat? Hello? Hello, am I audible?
Yes, sir. Yes, yes.
How much time do I have, Professor Shadabat?
Madam, you are on mute.
How much time do I have?
Sir, you can proceed another 10 minutes. Sir.
Okay, fine. Okay. The estimation of reliability for S out of K system under system setup based on bivariate generalized distribution. Okay, so this involves combining the multi-component system model with a bivariate distribution. See, we consider a system which has K independent and identically distributed strength components, each of which consists of a series structure of two dependent elements exposed to a common stress. So the system functions if S or more components simultaneously operate. So here we have a K system, K independent components in the system, and each component is made up of two dependent elements exposed to a common stress. So that is bivariate. So these kind of situations may occur oftenly in the real life. So for example, in suspension bridges, the deck is supported by a series of vertical cables. Cables hung from the towers. Suppose we have a suspension bridge consisting of n vertical cable pairs. One vertical cable pair consists of two cables on both sides of the deck. The bridge will only survive if a minimum of K vertical cable pairs through the deck are not damaged. So when subject to stresses due to wind loading, heavy traffic, corrosion, etc. So this is an example for the bivariate situation. So now, how can we handle such a situation? So here the estimation of reliability of system with k independent identical components whose operation is subject to a random stress is considered. The life of each component of the system is constructed by a pair of dependent elements. The strength of the components represented by a pair of random variables is assumed to follow a bivariate generalized Rayleigh distribution, and each component is exposed to a common stress P, which has a generalized Rayleigh distribution. So the system is regarded as operating only if S out of K strength variables exceed random stress. The estimation of system reliability is studied using maximum likelihood and Bayesian approaches. The maximum likelihood estimators are derived under simple random sampling, of course, ranked short sampling schemes, and Bayes estimators have been developed using Lindley approximation. So the reliability estimators are compared using whereas. Okay, so let us just look into what is how do we construct a bivariate generalized Rayleigh distribution. So Dina and Hardy 2013 proposed this bivariate generalized Rayleigh distribution, which is described as below. So we have three univariate generalized Rayleigh distribution random variables. This I can denote it as GR lambda 1 gamma, GR lambda 2 gamma, and GR lambda 3 gamma. And all three distributions are mutually independent. So what I mean is V1, V2, V3 are mutually independent, having generalized Rayleigh distribution with different scale parameters and common shape parameters. Okay, so now the probability density function of generalized Rayleigh is given below. And now to construct bivariate generalized Rayleigh, so what they did is they transform this x variables as x is equal to maximum of V1, V3 and y equal to maximum of V2, V3. So then the distribution of xy is bivariate generalized Rayleigh distribution with parameters lambda 1, lambda 2, lambda 3, and gamma. It has 4 parameters and is denoted as BGR. So if xy follow BGR with parameters this, then the density function is given by fxy is equal to this. And where lambda 1, lambda 2, lambda 3, gamma are greater than 0. And here you can see that this is not absolutely continuous. So now let T Z1, Z2, K be independent. And I'm sorry. Okay, now the strength vectors. So I have a bivariate sample like this: x1, xy1, x2, y2, so on, xk, yk, assumed to follow BGR, that is the bivariate generalized Rayleigh. And now let me transform this. Let me get a univariate sample by transforming it like this: zi equal to minimum of xi, yi. And then what happens is zi follows generalized Rayleigh, univariate Rayleigh, and a common stress T is distributed as again generalized Rayleigh with different parameters delta and gamma. So the system is working if, as I told you, S out of K of zi strength variables work. Okay. Now, so now once we transform this x1, y1, x2, y2, xk, y2, zi, z1, z2, zk, then we get a univariate sample from generalized Rayleigh, and we get the system reliability like this of sort of K system like this, and the other procedures are same. Okay, we obtain MLEs under simple random circle scheme, ranked set sampling scheme, and also the Bayes estimators are obtained. In this case also, a Bayes estimator requires approximation, that is we use Lindley's approximation, and for MLEs, to obtain MLEs, we have to go for iterative techniques. So, and again, simulation study is conducted, and the results which we get are base estimator is better. Base estimator is better, slightly better than RSS, and the simulations results indicate that MSEs for estimators of RSK decreases as the sample size increases. The MSEs of ML estimator are greater than that of base estimator for the priors considered in this here. And also in this study, MSEs of ML estimators based on RSS is lesser than the ML estimators based on SRS, indicating superior rate of estimation under RSS. Okay, I think I cannot move on to the next last part of the this thing. So I will just wind up. There is another distribution that is, we have considered here, that is the transmuted exponentiated inverse value. So that I am skipping, and I am just, I will stop here. So these are some of the references that we have used. Thank you. So this talk is a combination of 2-3 papers which are published with my research scholars. Plus like Shubhashri Joshi and Kavita.
Sharda Bhatt madam, unmute madre. Sharda Bhatt madam, unmute madre. Huh?
Ask to unmute. This, not that. This one. Yes. Yes.
Hello.
Hello.
Yes, madam, you are audible.
Yeah. Pandit sir, I am very sorry. I was muted from the organizer's end, so I was unable to talk to you about the timings in between. Indeed, it was a very nice and clear presentation. And I saw a message here. I think Professor Biradar wants to ask you a question. Can you, organizers, please unmute Professor Biradar?
Yes, madam.
Yes, Professor Biradar, sir.
Thank you, madam. Thank you for unmuting me. Can you hear me?
I'm here.
Am I audible, Professor Pandit?
Yeah, you are audible to me.
Yeah, it was nice lecture, Professor Pandit. Congratulations.
Thank you.
Yeah, I have a question.
Yeah.
Yeah, it may not be a question, it is my observation.
Yeah.
So in RSS, what we do is usually we to get a sample of size n, RSS of size n, we place n squared items on test. Okay.
Okay.
But usually in RSS, we assume that the cost of observations are almost negligible.
Okay.
But in case of live testing, you cannot say that actually. It will cost something. So is it feasible to have RSS in live testing? Because you cannot say that the cost is negligible or there is no cost. That is one thing.
See, the use of RSS. That is one of the.
I have another question.
Criticism on using RSS in case of live testing experiments. Yeah, I agree.
Yeah, that is one thing. The another thing is that suppose one is affordable for cost also.
Yeah.
My next question would be, how do you implement RSS for live testing? Because how do you judge that for each sample set, for each set, how do you judge the smallest one, the remaining are larger than that? Remaining lifetimes of the remaining units are larger than that. For example, from the first set. From the second set, how do you ensure that the one is smaller than the remaining n-2 are larger than that? How do you implement RSS in live testing?
This is one of the major concerns that I can understand. So in this, what we have done is, we have considered this as two different,
yeah, because all the examples you have coded, they cost
one
something.
Of the concerns for a live testing experiment in particular. Other places, I think I agree.
Yeah, this is my observation.
We can do that.
Not answer this.
Yeah, but in live testing,
my observation for all those
difficult.
Whom you have cited papers on this live testing.
Almost all the papers
using RSS.
Yeah. Hello.
Yeah. Okay. Go ahead.
No. Please repeat. This is a good suggestion for me. Yeah, that's why. Sir.
Yeah. Okay. Fine.
No.
Go ahead.
Okay.
Yeah, these are my observations. Just I think I leave to you.
No. Second observation I could not hear. Can you please repeat?
The second observation is even one is affordable for the cost of to certain cost. Now, how do we implement RSS in live testing?
Yeah. That's what I'm telling you. So I'm not sure how we can do that. So that criticism I have to look into. This
because, for example,
matter of just theoretical interest.
To have a lifetime of to observe a lifetime of 5 units, you have to observe, you have to place 25 units on live test and you will discard 20 of them.
Yeah, it will be.
But how do you discard that? How do you implement it?
Yeah, that's what I mean. The answer would be we have not thought of that.
Okay.
Just as a theoretical interest, we have done that. Applicability we have not thought of. Thank you for bringing it to our notice, and I will just think over it. If it is possible, whether it is possible or not. Yeah.
Okay, that is fine. Thank you.
Okay, keeping in time in mind, I think if anybody else has question, they can directly contact Professor Pandit later on. So I think on behalf of the organizers and delegates of this national level conference on statistical modeling and inference, I thank Professor Pandit for sharing his rich knowledge and research output on stress and reliability models using inversion distribution, generalized Pareto distribution, and bivariate generalized distribution. Thank you, sir.
I would like to thank the organizers for this giving me this opportunity, and also I thank Sharda Bhatt madam for chairing this session, and I particularly thank Professor Bihadar for bringing the crucial things to my notice. Thank you, sir. Thank you very much.
Thank you, one and all.
Thank you, madam. Thank you, sir. I wholeheartedly thank Dr. Sharda Bhatt for spending their precious time with us. Thank you, madam. I also thank Dr. Parmeshwar Pandit for sharing all the knowledge with us. So on behalf of PC Jabin Science College, Hubballi, and Department of Statistics Organizing Committee, I once again thank you for your valuable presence, madam and sir. Thank you. Now, it's my pleasure to introduce Chairperson of this session, Dr. Srimati Sujata Ingin Shetty, Professor and Chairman, Department of Statistics, Gulbarga University, Kalburgi. She has completed her MSc, PhD, and she is an active life member of Indian Society for Probability and Statistics. She has published about 20 research publications and has attended more than 20 conferences and workshops. She has guided a number of MPhil, PhD degree awardees. With this brief introduction, I heartily welcome Srimati Sujata Ingan-Shetty. I welcome you, Madam. I also welcome the invited speaker of this session, Dr. Srimati S.B. Munoli, Professor, Department of Statistics, Karnataka University, Dharwad. I welcome you, Madam. So now I request Srimati Namrata Batli, Assistant Professor, Department of Computer Science, to introduce the invited speaker. Over to you, ma'am.
Good afternoon, everyone. On behalf of PC Jabin Science College and Department of Statistics and Organizing Committee, it gives me immense pleasure to introduce today's session speaker, Srimati Dr. S.B. Munoli, Madam. She has done qualification in MSc, PhD in statistics, and she is presently working as a professor of statistics in KUD, Dharwad. Her area of interest is reliability theory modeling, assessment, stochastic processes, and their applications. She has published about 31 papers, and she has also written a book that is chapter number 1. And she has written popular articles, about 7 articles. In that, one article has been bagged Masti Venkatesh Iyengar Memorable Prize awarded by National Aerospace Laboratories in 2009. And she has guided 3 PhD students, and presently she is guiding 2 people. And she has attended conference and seminars about 35. And she was also invited speaker at conference about 10. And she is also resource person at number of workshops and special lectures delivered in other universities, about 11. And she has also done the service as a chairperson of department BOS, BOE, and she is also a coordinator of UGC, SAP, BSR project and committees of NAC, IQSE, convocation, and she has been warden of ladies hostel also. And she has also worked as a member examiner on BOS and BOE for various universities. I welcome you, ma'am, on behalf of Department of Statistics and PC Jabin Science College. Thank you, ma'am.
Thank you, madam. I request Dr. Sujata Ingan-Shetty, ma'am, to proceed the session.
Am I audible?
Yeah, ma'am, you're audible.
Am I? Okay. Good afternoon, everyone. First of all, I would like to thank the organizers for giving me this opportunity to chair the session, second part of a first session. So, Professor Surekha ma'am, are you there? Professor Surekha ma'am?
Surekha.
Yeah. So, in the second part of the first session, we have with us the speaker, Professor S.B. Munoli, who is a very good friend of mine and classmate also. Okay. So she's going to deliver her talk on probability distributions and their applications. Okay. So I welcome you and I invite you to deliver your talk. Professor Surekha Munoli.
Thank you, organizers. Thank you, Sujata, and thanks for a nice introduction about me. Before I start with the discussions, my intention of this discussion is The target group is undergraduate students of statistics, with the hope that this will motivate them for taking up higher studies in statistics. So here, what I am presenting is not of a research level or nothing like that, but that the UG students can understand some part of this discussion and they may take up interest in statistics. Okay, so let me start sharing my screen. Yes. Desktop. Yes. Okay. Statistics, we all know. At the beginning of this discussion, some preliminaries about distributions, very briefly, that is to complete the story, I will consider. And maybe at the later part of this discussion, let us discuss about some higher level applications of few distributions. Okay, so we all know that statistics is a collection of effective tools that helps other sciences to find the truth in the relevant areas. It supplies sufficient materials in being as accurate as possible to the findings of the reality. Usually we are expected to take decision about a group most of the times only in the presence of partial information. Such situations can be handled only with statistical tools. So we know that statistics existed with the very existence of human beings. The logic, the experience, the intuition, and the experiment together give a basis for statistics. The point to be noted is that statistical results are true to a group, but not at individual levels. Coming to statistical models, we use many statistical tools in several applications. The tools may be like descriptive statistics, estimation procedures, testing of hypothesis. These two together, generally we call it as inference, time series analysis, and many more can be added to the list. That is, we have several tools of statistics. Okay, all these tools are governed by certain assumptions. If these assumptions do not hold good, our analysis goes wrong. One of some examples, say one of the important assumptions is about underlying the statistical model is regarding the probability law. That is while proposing the technique. For example, in ANOVA, it is assumed that observations will have normal distribution and in chi-square attribute test, the assumption is that the data or observations can be classified into several mutually exclusive groups. Here we shall discuss about various probability laws, that is distributions, and in what situations they are used. As we know, our observations will be either discrete or continuous. Okay. So, as we know, our observations, when they are whole numbers, they are called discrete variables. And when they are real numbers, that is numbers with the decimal points, they are continuous. And we claim that many of the random variables like lifetime, age, height, weight gained, dose level, marks scored, etc. are continuous random variables. But if we talk in terms of numbers of completed cycles of operation, number of days for recovery, number of emergency admissions, number of survivors, number of missing teeth, etc., are discrete random variables. In analyzing data related to these observations, we use some statistical tools. And the first step to judge which probability distribution to consider for our data. The question is whether to develop the probability distribution out of experience or it is to be assumed on the basis of theoretical considerations. Say, for example, if we are considering the number of accidents per week on a busy road, say recorded for 30 weeks, say if we observe no accident for 1 week and 1 accident for 5 weeks, say this data we have out of the experience. That is the number of accidents. Maximum was 8 and this is the frequency, that is the number of weeks that had so many number of accidents. And out of this data we can formulate the relative frequencies, and when these relative frequencies are plotted on a XY plane, we get that is a rough idea about the distribution that our data follows. Okay, so here this is the development out of our experience, actual experience. But we can propose, by considering theoretical considerations, we can model this data using some existing theoretical distribution, or we can define our own effects, functional form to this probabilities or relative frequencies. And there are some commonly used discrete and continuous distributions. And Bernoulli trial, as we know, the Bernoulli trial has only 2 outcomes, like success and failure, effective and non-effective, presence or absence of a particular characteristic, etc. But when a Bernoulli trial is repeated n times, out of n trials, the number of trials that the success is observed is a binomial distribution. And the extension of this, that is, Bernoulli trial has only 2 outcomes. But if our experiment has, say, more than 2 outcomes, then we may have trinomial distribution, or more than 3, then it may be a multinomial distribution. So here, if an experiment results in k mutually exclusive outcomes, okay, then we have a multinomial distribution. For example, when a patient is admitted to a hospital, the patient may be cured of the disease completely, or partially he may be cured, or the severity might have increased, or develop other complications, or discontinue with treatment, or the patient may succumb to the disease, that is die. So these are the possible outcomes. Okay, suppose we have n patients at any particular time, then out of these n, how many have that is recovered, how many have that is left the treatment, and how many have succumbed, all this, that is, counts will be realized values of multinomial distribution. And the probability mass function for multinomial distribution is this, and this is that is somewhat extension of binomial. That is, binomial we have only 2 outcomes, so n factorial divided by r factorial and n minus r factorial we used to get there. That is probability that x equals to r. But now here k outcomes mutually, which are mutually exclusive. So this is the part and these are the probabilities with the respective frequencies. And here we have P1 plus P2 plus Pk as 1, and x1 plus x2 plus xk is n. Okay, example that explains this PMF is, suppose we have a sample of 100 individuals. What is the probability that this group consists of, say, 35 people having a blood group A, 33 having B blood group, and 22 having AB blood group, and 10 having O blood group. So this is the counts for different blood groups, and this is the corresponding probability. Okay, and geometric distribution, we all know this is called as waiting time distribution, and the random variable here is the number of trials required to get a success. So we can have a real life good examples for this: number of attempts to get through an IAS mains, number of World Cup finals lost before a success in the finals. The extension of geometric distribution is negative binomial distribution, and this is used as accident proneness model, and it is a mixture of Poisson distribution. And Poisson distribution, this distribution is used in the situations where the sample or sample unit is very large and P, the probability of occurrence of an event, is very small. Some examples where the Poisson probability law is used is, that is, number of alpha particles emitted by a radioactive substance that enter a prescribed region during a prescribed interval of time. So here the number of particles emitted will be infinite, and that it enters a particular small, you can say, aperture or so, that is very, very small, that number would be, and the probability will be very small. So we can model this event by a Poisson probability law. And next, one more example out of this is the number of defects on large manufactured article having many spares, such as aircraft. We all know that the aircraft's a very expensive affair, and it will have several sub-spares or spares, and national security, national prestige, everything is involved there. So with utmost care, this kind of our systems are manufactured, and probability of finding the defect in such units is very, very small. So this event, that is the number of defects in aircraft, will follow a Poisson probability law. And number of live insects found per square area of field after spraying an insecticide. So that is, we know very well that insects in fields, that is infinite number will be there in fields, and insecticide are manufactured to kill the insects. So to promote their insecticide to be very effective also, the manufacturer will give a bit higher dose as the using dose or prescribed dose per hectare or per acre, whatever it is, or per plot. But the farmers will also be very insecure, and because of that, again, they use more than the prescribed level. So finding an insecticide alive after spraying the insecticide is a very small probability. So again, this event is modeled by Poisson distribution. And one more example of Poisson distribution is number of insurance claim in some unit of time. Say any particular policy, lakhs together people would have purchased it. Out of that, those who have purchased it, very few will come for the claim. So this is again a Poisson probability model example. So next is hypergeometric distribution, one of the discrete distributions which has very good usage in ecology, and in forest department also. So here it can be proposed like this, that is a lot contains n, capital N units, of which m are defective. So out of n, if m are defective, then n minus m will be good units. And suppose we take a sample of n units from this lot, and the probability of s defectives in the sample, that is in out of small n, x defectives is given by this, where x takes the value 0, 1, 2, minimum of n and m, because the sample is n, and in all the lot itself contains m defectives. So our x should be minimum of n and m. And this is used in acceptance sampling plans. Most of our undergraduate students has realized this application of hypergeometric distribution in acceptance sampling plan. The other application of hypergeometric distribution is in ecology. To estimate the number of animals in a thick forest, number of fishes in a pond, number of birds migrated, etc. And note that in all these three examples, having a head count is not possible. Okay, so the population is to be estimated but not counted here. The assumption is that is, even whatever the estimation procedure, the statistical tool is used here, the assumption is population size remains constant for the duration of the enumeration. Of course, we may find some deaths and births during the time of enumeration or period of enumeration, but we can assume that they nullify one another. Okay, so that is the population remains constant during the period of enumeration. This is the assumption. Here the aim is to estimate the total number of animals, say capital N. So out of N, first m units or m birds or m animals are sampled, and they are marked. Say marking maybe by tagging them. Okay, and then again they are left to mix with the population again. Okay, so after sufficient time has elapsed so that these tagged or marked animals are thoroughly mixed with untagged animals, then a sample of n units or n animals is considered. So out of this sample n animals, let x be the number of tagged animals. And now we want to estimate the capital N, that is size of the population. And here this x follows hypergeometric distribution, and the population size can be estimated as that value which maximizes the probability mass function, that is MLE, you can say. Okay, so that is MLE for hypergeometric distribution. MLE for n of hypergeometric distribution is given by m into n by x, where m is tagged animals, n is sample size, and x is number of tagged animals out of the sample. Okay, so now let us move on to some important continuous distributions. And an essential property of a continuous random variable is that there is zero probability that it takes any special or any particular value. But in general, a non-zero probability calculable as a definite integral of a probability density function that it takes a value in specified intervals. Okay, so the simplest continuous distribution is exponential distribution, which has innumerable applications. Okay, and exponential distribution is used in reliability analysis. It is used to model lifetimes of electronic goods. A particular property of exponential distribution is lack of memory property. That is, whether a unit is a good new one or a used unit, its functioning remains the same, or the probability of failure remains the same for new unit or the unit which has been used for some time. So this is what we call it as a lack of memory property. This means that the failure rate is independent of time or the age. Okay, so another form of this exponential distribution is the exponential distribution with location parameter. And this form is used when we are guaranteed of minimum life of a unit or minimum time of recovery. Say any phenomena where the minimum time is guaranteed, there we can use it. Or even some insurance policies and all, that is, even if they are unit linked. So if by investment some money, then a minimum return amount is guaranteed, then in such cases also exponential distribution can be used. And gamma and Weibull distributions, again, these are used in life testing or survival analysis, reliability analysis. And Weibull distribution is very extensively used in insurance sector also, where the human life, that whole life cycle is a mixture of three failure rates. So Weibull can be considered for different shape parameters, that is shape parameter being in three different cases. We can have the whole life table of, or the failure rate of the human beings can be represented by Weibull probability law. And the next continuous distribution that we are considering is normal distribution. And the importance of normal distribution in the field of statistics is indisputable. The variables like intelligence, scores of manual dexterity test, weights of experimental animals, duration of illness, total number of ridge counts for the 10 fingers of an individual, the capacities of cranial cavities, cholesterol levels, blood pressure levels, fasting blood sugars, postpartum blood sugar level, serum protein bound, iodine levels are modeled by normal distribution. We can have infinite number of variables which can be modeled by normal distribution. And in many cases, the characteristic of interest takes only positive values. So in such cases, the truncated normal distribution is used. So we should know what is meant by truncation. By truncation, we mean some potential observations are missing from the population. That is, we want our sample to be from, or to have a particular value, or then only we can continue with our experiment. In such cases, we can use the truncation. That is, some potential observations are missing from the population itself. And if some observations are missing from the sample, then that sample is called censored sample. So here the population frame has the units, but that is being included in the sample, but we cannot take observations on those samples, maybe repeatedly by visiting the respondent or the experimental or the sample units we may lose because of climatic conditions and all. So then it becomes censored sample. Okay. So in case of discrete distributions, the common form of truncation is omission of zero class. That is, the observational apparatus becomes active only when at least one event occurs. So the corresponding popular truncated distribution in case of discrete distribution is zero truncated distributions. For zero truncated binomial, we have this probability mass function. Note that here x takes the value from 1 to n, and this denominator is probability that x will not take the value at 0. This is, and this is for Poisson. This is zero truncated Poisson distribution. So all inferential properties for these truncated distributions of Various distributions are also available in literature. So when we are talking about truncation, censoring, and then censoring of distributions, we can discuss about mixture of distributions also. So mixture of distribution means that is here as an example, I already discussed the human life cycle or mortality rates of human beings throughout the life cycle will have three different distributions, we can say. See here, it is a decreasing failure rate. Here we have a constant failure rate, and in this range, it is a increasing failure rate. So this is called as early failure rate, and this may be because of the hereditary reasons. These are accidental failures, and these are wear out failures. So this is a mixture of distributions, and Weibull has this property, that is for three different shape parameter values, it is combination of all these three. So we can have mixture of, say, exponential and normal, mixture of the different beta distributions, and for even discrete also we can have a mixture of distribution. So next continuous distribution that we are going to discuss is about uniform distribution. That is an alternate name for this is rectangular distribution. And these are special cases of beta distribution. This is beta PDF. And in this, if you substitute P and Q as 1, we get a PDF of uniform distribution over the range. Sorry, it has to be minus A minus H to A plus H. Okay, so this is denoted by uniform over A minus H and A plus H. Okay, so we can have different forms of this uniform distribution. And for this uniform PDF, the corresponding distribution function would be this. And the name is based on the appearance of the PDF. That is, it takes the fixed value for its support. Okay, so because of that, we call it as a rectangular distribution. And alternative to this, that is the one which we had defined, we have this also as our uniform distribution in the interval alpha to beta. And for alpha equals to 0 and beta value as 1, or alpha as minus half and beta as half, we have standard form of uniform distribution. Okay, that is standard uniform distribution. And uniform distribution over the interval 0 to theta has this PDF. And this also will have the same PDF. And the standardized uniform distribution. Note the difference between standard uniform distribution and standardized. A standardized random variable means when we subtract mean from the random variable and divide by the standard deviation of that distribution, that is called as a standardized random variable. So the standardized uniform will be of this form, and standard uniform will be of this form. Okay, if y is uniformly distributed over 0 and 1, then if we have this transformation, that is x equals to √3 into 2y minus 1, then x will have standardized uniform distribution. Now, to discuss about the origin of standard uniform distribution, we have this. So during the later part of 18th century, Bayes, and earlier part of 19th century, Laplace coined the term uniform distribution. The uniform distribution with A equals to 0 and H equals to half into 10 to the power minus K is often used to represent the distribution of round of errors in values tabulated to the nearest k decimal places. Say if this 10 is replaced by 2, then it is the round of error of a binary number system. Okay, so x minus a, the symbol, that is whatever the value we give in square bracket, is round of error of x in units of a. Okay, where this denotes the integral part of x by a. Okay, so if x1, x2 are independent random variables with characteristic function, say phi, then for any positive integer, Nagav and Makim have shown that the necessary and sufficient condition for say this value, that is the supremum of this probability as n tends to infinity, is given by x by a is this. Okay, so further Holovin have showed that if limit as n tends to infinity is 0 for k equals to 1 to so on, then the round of errors will have unit uniform distribution, that is standard uniform distribution. Okay, a uniform distribution also arises as a result of the probability integral transformation theorem. And this theorem is very useful in generating random numbers from any distribution. And this theorem is stated as if x has continuous variable with distribution function fx, then fx, note here a random variable x, will have unit uniform distribution. And this result can be proved very easily. So letting fx as y and x following f distribution. So if g is the distribution function of y, then basic definition of distribution function, so gy will be probability that y is less than or equals to y, and our y is fx. So we have this, and this probability can be written like x less than or equals to f inverse y. And note that x has the distribution function f. So this will be f inverse y, and this is y, which is nothing but the distribution function for standard uniform distribution. Okay, so this result has many applications. The expression for generating functions, moments, characteristic function, order statistics, and other distributions, Lorentz curve, Guinness index for uniform distribution are in closed form, and so it has got very huge application. And characterization of uniform distribution, we have that Hamdan proved that x is uniformly distributed over 0 and 1 if and only if this is the condition. And Peirce provides the alternative characterization of the type, that is a random variable x has uniform distribution over 0 and 1 if and only if for alpha lying between 0 and 1, this is the case. Okay. So the other characterizations for uniform distributions are provided by Terrell, Abdelhamid, Zakli and Murray, Lin, Ashanullah, that all these have provided characterizations for uniform distribution. So related distributions of uniform distribution are beta, exponential, Bates, standard triangular, tin, Dirichlet, etc. are the related distribution. And we have mixture of uniform distributions, and they also have good applications in the literature. Okay, uniform distributions are utilized in connection with sample quasi ranges, stratified sampling, power functions of tests, accident proneness model, etc. It has application in physics, life testing, etc. It is used to model residual lifetime after age X in insurance. Insurance is a sector wherein one is very much interested in remaining lifetime of the individuals. That is, if a person purchases the insurance policy when he is aged X, the insurance will levy the premium or fix the premium based on the remaining life. Okay, so that is the remaining life. If T is the total expected life of an individual, then T minus X will be the remaining life of the individual at age X. So here the remaining life is modeled by the uniform distribution. Okay, Allen has applied uniform distribution to form a model of the distribution of traffic along a straight road. So this is a very good application of uniform distribution, we can say. And the result is also very interesting. Here, if P is the probability that one vehicle in the interval of length H, here the assumption is that a road is subdivided in different, subdivided in different parts. Each part is of length H. Okay, so if P is probability of finding one vehicle in the interval of length H, and Q is probability that no vehicle in that length or in that interval, which is of length H. And probability of finding more than one vehicle in the interval of length H is negligible. And also, to prove this result, it is assumed that the length of the vehicle is negligible compared to length of the interval. So the whole road is subdivided in parts of equal length of, say, H, and assuming that there are K such intervals between two vehicles, K may be 0, 1, 2, so on, and the distribution, if the distance between the two vehicles is given by T, then that would be HK. H is the number of intervals between, H is length of the interval, K is the number of intervals between the two vehicles. X1 is the distance of the vehicle from the starting point of that interval of, say, vehicle A, and X2 is the distance between the starting point of the interval in which vehicle B is there to where it is. So these are the two random variables, and H is the width and K is the number of intervals. And note that here K follows the geometric distribution and X1, X2, as per our assumption, follows uniform distribution over 0 and H. Okay, so here the distribution of, say, S, which is X1 plus X2, is this, again using the property of uniform distribution. This is obtained, and we want to know the distribution of the distance between two vehicles, which is HK plus S, and this probability is given by, that is T belonging to some small interval, and this capital T is HK plus S, and this event is equivalent to this. Here note that K is a random variable, so this probability can be written as the same probability K replaced by small k, that is conditioned with K is realized as small k into probability of K. Okay, so we know the distribution of S as this. So now in place of S, we have this T minus HK. So using this, we get the distribution of T in this way. So this is for different values of K. When K is 0, we get the interval to be, that is T value to lie between 0 and 2H. And again, using this probability, we have when t lies between 0 and h, this value, and when t lies between h and 2h, we have this value. Okay, so these two are the values for t lying between 0 and h and t lying between h and 2h. Combining these two, we get this distribution, that is PDF in the interval 0 to 2h. Okay, so for different values of k, we can write this, and at the end, the distance between two vehicles on a road is modeled with this probability. Okay, so this is very much applied by many countries, this law, to control the traffic or to study the traffic. Okay, so many statisticians and mathematicians have presented algorithms for generating uniform order statistics. These algorithms can be used to generate order statistics from many other continuous populations through the inverse CDF method. Okay, since it is order preserving. And Balkrishnan and Sandhu proposed simple and efficient simulation algorithm for generating progressive type 2 censored samples from the uniform 0-1 distribution. So at the beginning of this discussion, we discussed about censoring. That is, if some potential observations are missing from the sample, we call it as censoring. And in progressive censoring, in general, n units are subjected to test. And after the first failure, R1 surviving items are removed at random from further observations. And after the second failure, R2 surviving units are removed from the test at random, and so on. Okay, so this process can be continued until some criteria is met with, usually half of the units are failed, or until all the units fail, again depending on the nature of the units that are subjected for the life testing experiment. Okay, and usually this type of sampling scheme is used wherein the units can be used even after they have functioned for some time, and they can be used later effectively or as good as new one. So that is R1 that have been removed after the first failure can be included in the lot that can be released to the market. In such situation, this can be used. Okay. So Balkrishnan and Sandhu have established that if y, okay, so y is defined in this way, where x1, x2, xm are the observations from what is that progressive censored observations, then these have established that ui, which is defined in this way, yi to the power I plus rm. Okay, so rm minus 1, so on, are the number of units that have been removed from the test. Okay, are IID uniform random variables. So another important continuous distribution that is available in the literature is extreme value distribution. We have 3 forms for this distribution. Okay, so where theta and k are parameters, the corresponding distribution of minus x is also called as extreme value distribution. Here x is an extreme value distribution for maximum, then minus x will be the distribution of minimum, which is also an extreme variable. So that is the property of these 3 distribution. And form 1 is most commonly referred to as extreme value distribution. And with these transformations, in form 2 and 3, these reduce to form 1 of extreme value distribution. Okay, and if you substitute minus x in place of x, we get Weibull distribution. The term extreme value is attached to these distributions because they can be obtained as limiting distributions as n tends to infinity of the greatest value among n independent random variables, each having same continuous distribution. So replacing x by minus x, limiting distribution of least values are obtained. Some applications I have listed here. Fuller and Griffith have used this distribution in the study of flood flows and rupture and flow in solids respectively. Gumbel used this distribution to model radioactive emissions and human lifetimes. Gumbel, in 3 papers, advocated this model in the study of flood discharges, estimation of flood levels, and forecast of floods, which is very important for administrators. Okay, Frankel and Kontarova used the distribution to study the brittle strength of crystals. The application to study earthquake magnitudes was pointed out by Nordquist, and while discussing factors influencing self-purification and their relation to pollution abatement. Abatement means to make something less strong. Okay, so Wells has used this extreme value distribution to model microorganism survival times. Epstein applied the theory of extreme values.
8 minutes for presentation.
So how much time I have?
Madam, you can conclude, please.
Okay. So it is also used in the 2 minutes. Studies of dielectric strength of capacitors. Capacitors means we know the devices that are used to store electric charges, and they are used in the study of gust load. That is, gust load means a sudden strong wind problems, rainfall data, fatigue, failures in solids. Okay, so we have mixtures of extreme value distributions, and our students, they are well versed with the what is that, sampling distributions, that is central and non-central chi-square TEF distributions. They have studied already, and their applications, they are vast. And we have double exponential distribution, which has very vast application. Okay, so there are bivariate versions of various distributions in the literature available, and these distributions have too many applications in survival analysis, and very recently studied distributions are like linear failure rate, McCam, Birnbaum, Sanders distributions. They are used in reliability engineering, and we know various variants of bivariate exponential. So Marshall-Olkin and Bloch and Basu bivariate distributions are also available. The important feature of Bloch and Basu is that it accommodates the simultaneous failure of units also when we are considering the experiments. Usually, when there is a multi-component systems experiment is conducted, it is assumed that the components do not fail simultaneously or at a particular time point. But this accommodates that feature also. So various statistical probability laws are available. They are applied in different fields, and one can explore these distributions for different studies. And with this note, I conclude my talk. And these are some references. Very few I have listed. So innumerable references or literature is available on this topic. Thank you. I thank the organizer. I thank the chairperson of this session, Sujata.
Dr. Sujata ma'am,
Am I
would you
audible?
like to speak something?
Yeah.
Yes,
Am
ma'am.
I audible?
Yes, ma'am.
Okay. So, any questions from the delegates? Any questions from the delegates? So, if there are no questions, then I would like to thank Professor Munoli for highlighting the practical applications of some important probability distributions. So starting with Bernoulli distribution, she has covered many discrete as well as continuous distributions like Poisson, hypergeometric, exponential, standard univariate distribution, extreme value distributions, etc. Your talk is very useful to the delegates, especially the undergraduate students. So on behalf of the organizers, delegates, I thank Professor Munoli for your enlightening talk. Thank you.
Thank you. Thank you.
On behalf of PC Jabin Science College, Department of Statistics, and the organizing committee, I thank Dr. Sujata Inginshetty madam for her precious time. And I also thank Dr. S.B. Munoli for sharing many interesting facts with us. Thank you, madam. Thank you, madam. It's my immense pleasure to introduce Professor Dr. Mk Patil, in charge principal, Padma Bhushan, Vasantra Odad Patil, Mahavidyalaya, Kavte Mahankal, Maharashtra. Sir has teaching experience of 35 years and has published 13 international journals, 11 paper presentations in national and international conferences, and has participated in about 70 workshops and seminars. He is a member of Board of Studies in Statistics, Shivaji University, Kolhapur, since 2017. He has visited various institutes in India and abroad and is an active member of many associations. With this brief introduction, I welcome Dr. Mk Patil, chairperson of this session. I welcome you, sir, and I request you to proceed this session. Over to you, sir.
Hello.
Yes, sir, you are audible. Sir.
Hello.
Yes, sir. Yes, sir. You're audible. Sir.
Audible, no? Okay.
Yes.
Thank you, madam. Good afternoon to all. Very much thankful to organization committee. They have given me the opportunity to chair this session. So there are 5.
So you're not visible, sir.
I'm not used that.
Okay, okay, sir. Okay.
Okay, we'll start this paper presentation session. There are 5 participants. Each participant have 10 minutes, 8 minutes for presentation and 2 minutes for discussion. So try to summarize your results within the stipulated time. First, I will like to introduce Dhananjay M. Kshirosagar to present his topic. Title of his paper is Non-Parametric GLR Control Chart for Processing Dispersion. Dhananjay Kshirosagar. Dhananjay Kshirosagar is present?
Yeah, I'm present.
Continue.
Am I audible, sir?
Yes. Yes, you are audible. You can continue.
Screen share is there, sir? Screen is there? My screen is visible, sir.
It is not visible. So green button is there, share.
Yeah.
Just click that and open that file.
Yeah. Okay. Hello.
It's now visible.
Okay. Welcome all of you in my presentation. This research work is done with Professor Dr. V.B. Gute, sir, Department of Statistics, Punyasloka Devi Holkar, Solapur University, Solapur. My research title is Non-Parametric GLR Control Chart for Process Dispersion. So, outline of paper is introduction, then the concept of GLR sign chart, statistical performance measure, performance evaluation, conclusion, and the last part is references. So, introduction. Control chart is most important and widely used statistical process control tool to monitor various processes such as industry, healthcare, education, etc. And we know very well, Seward in 1931 introduced a memory-less control chart, which is highly effective for detecting large shift in the process parameter or parameters. However, it is less effective for detecting small shifts. On the other hand, memory-based control chart is the best alternative to the Seward chart for detecting small shifts, namely the cumulative sum control chart, that is Kusum chart, which was developed by Page in 1954, and exponentially weighted moving average EWMA control chart, which was developed by Robert in 1959, and these two charts are more effective in detecting small shifts. However, they are less effective for detecting large shifts than the Seward charts. Now, control charts based on generalized likelihood ratio statistic is superior alternative to Seward, Kusum, and EWMA charts when the interest is quick detection of small as well as large shift. Most of the control charts in the existing literature are based on certain assumptions about to the distribution of process output. That means when we know sometimes when we know the underlying process distribution, then we can continue our process immediately. But sometimes what happens, however, in practice, sometimes such assumptions are violated. In such case, we refer or we move to non-parametric or distribution-free control charts, which are become popular in some recent years. These charts, means non-parametric control charts, do not require any assumption about the underlying process distribution. In the present work, we have proposed non-parametric GLR control chart for process dispersion. So some review literature of the paper. Sina and Venkaman in 1995 were the first proposed to GLR control chart. In that paper, they proposed a GRR chart for mean of normal process. After a long time, in 2010, Reynolds and Lau considered the problem of detecting small and large shift in the location of normally distributed process. Then, Hyong et al. In 2012 proposed a binomial GRR chart for monitoring the proportion and extended the idea by Hyong et al. In 2013, a binomial chart used for Bernoulli process. Then in 2012, Lee proposed the GRR control chart for Poisson distributed process with individual observations. Again, Reynolds et al. In 2013 proposed the GRR chart for simultaneous monitoring mean and variance of a normally distributed process. Then Hubballi in 2018 provided a review of various GRL control charts in case of count data processes such as binomial, Bernoulli, Poisson, and multinomial process. Some review of the non-parametric control charts, that is, which are already not mentioned here, but we advise to refer Chakraborty et al. In 2001, Q&E in 2012, Q&A 2018. These papers are most important for non-parametric control charts. Some of the non-parametric control charts based on science statistics, for example, in 1995, proposed the one and two-sided Seward sign chart, and also they proposed a one-sided Kusum sign chart. Then Yang and Cheng in 2011 proposed a two-sided Kusum chart. They again, furthermore, Yang in 2011 introduced an Imua sign control chart, and Abbasi corrected in 2012 its control limits and modified the paper. Recently, Mahadika and Godse proposed the SPRT sign chart. So some non-parametric control charts based on science statistics are here. Then what is the concept of GLR chart? So we know very well, GLR recently, people are emphasis on GLR control charts. And what is the exact procedure of GLR control chart? It is the parameter estimation method. It is also called as fault detection method. There are three main steps to develop the GLR statistics. First step is to obtain the likelihood function for the null and alternative hypothesis. Second step is substitute the maximum likelihood estimator for dispersion or location, if you location into the likelihood function for the alternative hypothesis. Then third step is take log likelihood ratio of two like functions. After simplification, we will get GLR statistic. Then we compare GLR statistic with threshold limits of the GLR chart. So you see here the procedure of GLR sign chart here. Let X denotes continuous quality characteristics whose dispersion is to be monitored here. Let Q1 and Q3 be the first and third quartiles of the observed distribution of X. When the process is in control, we assume that Q1 and Q3 are known. Then a sample of size n is taken at a regular interval of time from the process. And after taking kth sample, we can compute Tk. What is Tk? Tk is equal to summation Sn Kj, j from 1 to n, and k is equal to 1 to so on. Where Sn Kj is equal to 1 if Sn Kj is less than Q1 or Xkj greater than Q3. Otherwise, 0 means the process is in control. We can assume that here 0. So Sn Kj follows Bernoulli distribution. So we know very well sum of Bernoulli follows binomial distribution. Same type of technique we can use here. Note that Tk follows binomial distribution with the parameter n and p. So what is p? P is the probability of Xkj less than Q1 or Xkj greater than Q3, and T1, T2, so on, Tr are independent. In this paper, we assume that the process is in control for the first tau samples. Tau is the process change point and it is unknown. and assignment cause occur between the samples tau and tau plus 1 shift unknown size in P. Let us denotate the shifted value of P by P1. Then we see that T1, T2, so on, process follows binomial with the parameter n comma p naught distribution, and tau plus 1, tau plus 2, so on. T follows binomial with the n p distribution. After kth sample, we can follow the procedure of likelihood. Likely is 2. Then next statistic to determine whether there has been a shift in P in the part of K sample is. Then we can take here log likelihood ratio of these two, and after simplification we will get lambda K is equal to maximize over 0 less than or equal to tau less than K, n into K minus tau in brick bracket, P1 hat into log, P1 hat into 1 minus P naught divided by P naught into bracket 1 minus P1 hat plus log of 1 minus P1 hat divided by 1 minus P naught. This is my GLR statistic, where what is P1? P1 is the estimated value, and which is equal to summation Ti. I take the value tau plus 1 to, and our interest is to detect increase in P, so that we consider P1 hat is equal to maximum of P naught comma summation Ti divided by n into bracket K minus tau. The calculation of lambda K requires T1, T2, so on Tk, so that the computation of Tk can be performed at each sampling point K.
Excuse me, sir.
Large.
Sorry to interrupt, but you have only 2 minutes.
Okay. When K is large, it may be computationally expensive to calculate lambda K. Then we can use here windows of the past M samples. The windows of M can be chosen such that the performance of the GLR chart with window is essentially the same as without window, and this statistic is as follows. Lambda Mk is equal to maximize over 0 less than T less than tau less than K, n into K minus tau, and into big bracket as above. If K is less than or equal to M, and other if K is greater than M, these two conditions are mentioned here. Next is, we can estimate the change point. Tau hat as an estimate of tau. We can estimate in this way. So the GLR sign chart signals if lambda K is greater than G, where G is the control limit of the chart, which is to be chosen such that the chart has reside in control performance. So statistical performance measure, we usually in control chart technique, there are two measures, zero state measure and steady state measure. In this paper, we use steady state measure. So steady state measure refers to the occurrence of a process shift at some random time following the start of monitoring. So performance evaluation system, before that we want to design of GLR chart, and then such design of GLR chart we can use in performance. So in
Sir,
performance,
can you please conclude the presentation? Okay.
Steady state average number of sample to signal with Seward sign, 3 Kusum charts and GLR charts. You see a table, these are the values, then Seward sign values, Kusum 3 Kusum values, and GLR sign chart values. So you can observe here, when P is greater than 0.85, there is very good shift occur in GLR sign chart. When G is equal to 3.4603, M is equal to 35, and tau is equal to 25. Table 1 demonstrates that SSC of GLR sign chart is smaller than of Seward sign chart for a shift of large size in P. Kusum chart is good performance when P is close to P1, but performance is not good for other values of P. Although, thus we conclude that the GLR sign chart has much better performance than the Seward sign and Kusum sign chart in detecting large shift. So conclusion, the GLR sign control charts For monitoring the process each person is studied, the performance of the chart is evaluated by using simulation. We observe that the performance of the GLR chart is better than the Shewhart sign and Kusum sign charts for detecting large shifts. And these are the references. Thank you.
And 20 minutes and you are not listening at all. So if any question from audience, they can ask him. Okay, there is no any question. Next presenter is V.K. Ghadge, Department of Statistics, Vigyan Mahavidyalaya, Sangola, District Solapur. Title of his paper is Distribution Free Lepage Type Kusum Control Chart for Joint Monitoring of Location and Scale. So V.K. Ghadge is present. And
Yes.
remember, Vijay Ghadge, remember that your time is 8 minutes. Whatever you want to present your result just in 8 minutes and 2 minutes for question or discussion. So please try to summarize your result in 8 minutes.
Okay.
Continue.
Am I audible?
Yeah, you are audible. Literature survey, it is not necessary
Good
to.
afternoon, everybody. Hello.
Okay, you
Hello.
continue.
Good afternoon to everyone. My topic of presentation is a distribution-free Lepage type Kusum control chart for joint monitoring of location and scale parameter with under the guidance of Dr. V. Woode, Director, School of Computational Science, PA Solapur University, Solapur. Now, introduction. The concept is introduction, determination of UCL, in control run length of this CLM statistic, out of control run length of this CLM statistics, comparison with CL chart and conclusion. A single distribution free and Shewhart type control chart on the basis of Lepage statistic is well known in literature for simultaneously monitoring both the location and scale parameters of continuous distribution when the both of these parameters are unknown. In the present work, we consider the single distribution free cumulative Kusum chart on the basis of Lepage statistic based on a Baumgartner and Ansari-Bradley statistic referred to the cumulative sum Lepage CLM chart. The proposed chart is distribution free and therefore the in-control properties of the chart remains invariant and known for all continuous distribution. Control limits are evaluated for implementation of both of the proposed chart in practice. And we compare this CLM chart with CL chart, that is a Shewhart type control chart based on Lepage statistic, another Lepage statistic based on Wilcoxon rank sum statistics and Ansari-Bradley statistics. And to find UCL, that is H for any given pair of n and m values, a search is conducted with different values of H. That value of H is obtained for which the error not is equal to the nominal target value. The result in table 1 gives the required H values for the target value error not is equal to 500 for various values of k is equal to 0, 3 and 6 respectively. And here we consider k is equal to 0 and is equal to 30, the reference observations and test samples of size m is equal to 5 are available and ARL is equal to 500 is desired. The value of H for the CLM chart is given by 96.407. Table 1, in table 1, charting constant H for the CLM chart for various values of n and m for some standard target value of ARL not 500 for n is equal to 30 and m is equal to 5. 30, 11, and k is equal to 0, we have these values of upper control limit h, UCL. And for k is equal to 3, we have these values, and for k is equal to 6, we have these values. The performance of the Kusum control chart is generally studied through its run length distribution, because the run length distribution is skewed to the right, and it is useful to come across the various measures such as mean, the standard deviation, several percentiles, including the first and third quartiles, to characterize the distribution. We consider both the in control and out of control setup. For the in control setup, we simulate both the reference and test samples from the standard normal distribution. We choose n is equal to 30, 50, 100 and 150, and m is equal to 5 and 11. For a given pair of n and m values, we obtain upper control limits h for nominal target value error net of 500 and simulate different characteristics of the in control run length distribution. The results are shown in table 2. It is seen that in control run length distribution is highly skewed to the right, and the target value error naught is larger than the median for all combinations of n and m, whereas third quartile is larger than 500 and 95th percentile is seen to be stable around 3 times the ARL naught 500. The performance comparison between CLM chart and CL chart for the normal theta delta distribution with ARL naught is equal to 500. N is equal to 100, m is equal to 5, and k is equal to 0. These are the shifts 0, 1, 0.5, 1, 1, 1, 0, 1.5, 0.5, 1.5, 1, 1.5, 0, 2, 0.5, 2, and 1 and 2. These are the ARL naught. That is 500.2, and this is the SDRL, and P5, Q1, Q2, Q3, and P95. This for normal distribution with parameter delta and theta and delta. Here notice it. And this is for Cauchy distribution. N is equal to 100, and m is equal to 5, and k is equal to 0. And we have these values of ARL naught. Compare with the CL statistic based on Bradley Ansari and Wilcoxon's rank sum statistics. And third is for log normal distribution. These are the values of ARL naught and SDRL and some percentiles P5, Q1, Q2, Q3, and P95. These are the results which are for only k is equal to 0. We also obtained for k is equal to 3 and k is equal to 6. For 500, ARL naught 500, for 200 and 370. A single non-parametric leafage type Kusum control chart called the CLM chart is proposed based on the combination of Baumgartner and Ansari-Bradley statistics for the joint monitoring of location and scale parameter of any continuous distribution. Charting constants are provided for CLM chart. Both the in control and out of control performance of the chart are studied. Various performance characteristics of the proposed CLM chart, the mean, standard, median, and some percentiles of the run distribution are examined and compared in simulation study with the performance non-parametric CL chart. It is observed that CLM chart performs better than the CL chart. The proposed distribution free CLM chart monitors the unknown location, scale, and parameter. Single chart maintains target value error naught for all continuous distribution and comes with summarized analytical properties. Procedures in case of a single to determine whether the shift is in location or scale or both. Most important, it does not all of these without requiring the practitioner to make the important assumptions of normality on or any other distribution. Therefore, the proposed chart can be useful in a wide range of practical applications. And these are the references. Thank you. Hello?
Yes, sir.
Okay. Okay, thank you.
Thank you, sir.
Okay.
Now I request Mr. Prakash S. Chowgle to present the paper, Department of Statistics, Rajashri Chhatrapati Shahu College, Kolhapur. And the title of the paper is Monitoring Linear Profile Using EWMA Control Chart. Sir, you can please go ahead.
Thank you, madam. Thank you for organizing, for giving me this opportunity for presenting my research work done under the able guidance of D.N. Kasid, Professor, Department of Statistics, Shivaji University, Kolhapur. The outline of this presentation is introduction, the simple linear regression, exponential weighted moving average, simulation, study.
Sorry to interrupt you, sir. Sir, the time limit is 8 minutes.
Okay.
Okay.
The various statistical process control techniques have been widely used to successfully apply to several industries monitoring linear profile. Monitoring the processing since W.A. Schwartz introduced the first control chart in 1924. Generally, there are two different approaches may be used. First is to identify the process state using the density function of single or multiple quality characteristic, and second is the profile or function quality characteristic. The quality of the process or product characterized by linear relationship between the response variable or one or more explanatory variable. This is relation is referred to as profile. In some application, profile can be well represented by simple linear regression model, but many times the complicated model are demanded. There are several types of profiles: simple profile, multiple profile, polynomial profile, logistic profile, non-linear profile. Profile monitoring is a relatively new area in statistical process control, but it is generally rapidly in statistical process control application. There are two phases called phase 1 and phase 2. In phase 1, by using historical data, we are find out the parameters of that control charts, and in second, the control limits established in phase 1 are used in second phase. There are a number of the first original control chart techniques based on control charts is done by Diapola in 1945. He combined the regression method with a conventional control chart. This control chart is called as correlation control chart. It is used to analyze the quality problems in airplane assembly. He used the regression equation to predict the rivot use the function of number of minor pair. Mendel 1965 extended the idea of correlation control chart to monitor productivity of postal workers. Jackson's and Weiss also discussed the issue of control chart when the process variables are related. Hang and Hockey in 1993 and 1991 suggested a model-based monitoring procedure, also called as regression adjusted procedure. Nader and other three examples express the term profile. Wade and Woodall taking a review of analysis of cause selecting control charts. Can and Albin proposed a multivariate control chart for monitoring intercept, slope, and linear profile. Team and others use three EWMA control chart for simultaneously monitoring the slope, intercept, and process standard deviation. Jackford and explored the GLM regression adjustment procedure, gamma distributed model. Gupta and others improve the performance of methods suggested by Kim and Mohammed and Udal applied the global F statistics to global F strategy based on indicator variable method for phase 1. Controlling the monitoring linear profile. Schickner and other used regression adjustment procedure and Mohammed and Udal the change point technique based on likelihood ratio test in phase 1. There are number of researchers doing doing these techniques for analysis of profile monitoring. We are go to next step, that linear exponential weighted moving average control charts. In the regression, the regression model is yi equal to beta naught plus beta 1 xi plus epsilon I, where epsilon I is our IID and standard normal variables, and the parameter beta naught and beta 1 are respectively slope and intercept, and sigma square are all are unknown, and these are estimated in phase 1 by using sample data. But in phase 2, we assume that they are known. The least square estimated beta naught beta 1s are given by this. Sample beta naught and beta 1 distributed with mean beta naught and beta 1 and their variance is sigma 1 square. Sigma 1 square into these are their mean and variances, and error is yi minus yi hat, and this is the MSC sigma hat square. This is sum of squares of error divided by n minus 2. We here take the model for yi equal to 3 plus 4 xi plus epsilon, and the regressors are generated from normal 5 and variance 1.5, and the random noise is taken from standard normal distribution and different heavy tail distribution, that is Quachi, standard Laplace, standard slash mixture of two normal, log normal, Pareto distribution, student T with 3 degrees of freedom, and we are selecting the smoothing constant lambda as a 0.5, 0.1, 0.15, 0.20, and 0.25, and the rational subgroup sample size is taken as 25, 50, 75, and 100 and 100. The control limit is chosen to get specified in control average length 370, and the replication 10,000 times by using R simulations, R software for simulation. We obtain the ARL. We obtain out of control ARL for EWMA control chart. This is the first table, the average run length of sample size 5 with lambda equal to 0.25, lambda equal to 10, and second table is the corresponding 25, sample size 25, and lambda equal to not 5, not 10.
So will sir come to the conclusion?
Yes. And the output of these in above tables from lambda equal to 0.5, 0.10, 0.15, the normal distribution shows an excellent performance to other distribution. Mixture of normal and Laplace and T distribution shows the best performance than log normal, Quachi, Pareto, and slash distribution. Lambda equal to 0.20 and 25, mixture of normal distribution show excellent performance than normal and other distribution. Laplace, student T, log normal, best performance than Pareto and Quachi, and slash control chart perform first for the other distributions. For detecting the moderate shift except lambda equal to 0.5, the normal distribution show excellent performance than remaining distribution. For Laplace distribution, control chart perform better than mixture normal distribution when lambda equal to 25 and the error distribution mixture normal variate. Control chart perform better than Laplace. Student T and log normal perform poorer than normal mixture of normal Laplace, but they show best performance Pareto than Quachi and slash distribution. For detecting the large shift for smaller values of smoothing constant, normal, Quachi, slash show excellent performance. For large smoothing constant normal, Laplace mixture of normal shows best performance. Also, the students T and log normal perform better than para 2. For investigating the effect of sample size, we have considered the sample size 25, 50, 75, and 100 and 150. From this table 1 to 5, it shows that for increasing sample size, the performance of out-of-control average run length is decreasing. And for decreasing the sample size, the trend of out-of-control ARL is increasing for all distributions. And these are the references. Thank you.
Thank you so much, sir. Now I request Mk Patil, Department of Statistics, PH Solapur University, Solapur, to present her paper. Title of the paper is Estimation of Change Point in Mean Control Chart for Autocorrelated Processes. You can go ahead, madam.
Yes. Are my slides visible?
No, ma'am. Sir, Prakash Chowgule, sir, can you please stop sharing the screen? Yes, ma'am.
Good afternoon, all of you. I'm going
Your
to...
time limit is 8 minutes.
Okay, thank you. I'm going to present my research work on estimation of change point in mean control chart for autocorrelated processes under the guidance of V.B. Gute sir. So these are outline of my talk: introduction, objectives, literature review, mean control chart for autoregressive process step change model, performance of the estimator, conclusion, and some references are included. So as we know, the control charts are the standard statistical process control technique used to monitor the manufacturing processes by distinguishing between the common cause and special cause of variation. So some traditional control charts are used to detect the process upsets like Shewhart control chart, EWMA, and Kusum chart. But generally it is seen that the process, it is assumed that the sampled process observations are identified and distributed. When the control chart signals out of control signal, then it is identified the change in the process, but control chart do not indicate the exact time when the process change occurs in the process. So for that, we can use the change point model. That is another approach which identifies the time of the change in the process. So generally the observations are assumed to be come from the independent IID normal distribution. So here we tackle the problem for the autoregressive processes where the observations are not independent. So our objective is to identify the time of change in mean for autoregressive process and to detect process shifts quickly and improve the quality of the process. So these are some literature review that Samuel considered the problem of identifying the time of step change with X-bar control chart. Again in 1998, he considered the problem to identify the change in the normal process variance. Alwan and Robert, they assume that the autocorrelated process can be modeled by an autoregressive moving average, that is ARMA model. Timur evaluated the change point problem in Kusum-based control chart for monitoring the level parameter of the AR1 process. So here, the mean control chart for AR1 autocorrelated data is considered. So equation 1 is the autocorrelated model. From that, the observations are considered. So epsilon t is the normal 0 sigma square and phi is the autocorrelation coefficient, which is less than 1. So the Alban and Radson give the standard deviation of the sample mean for AR1 process. So from that, the LCL and UCL from the mean control chart for AR1 autocorrelated process are given by the equation this LCL and UCL. And the term psi is given here. So for evaluate this process step change model, we assume that the process parameter mu of the time series model is initially in control with a known value of mu naught. However, after an unknown point in time, a change in the process, that is when change occurred in the process, that in control mean shifted to the mu1, which is mu naught is equals to delta sigma upon square root of n, where n is the subgroup size and delta is the unknown magnitude of the change. So here we assume that once this step change occurs in the process parameter, then process remains at the new level of, that is as at the changed process parameter mu1 until special cause has been identified and eliminated by taking the corrective actions. So here we consider the control chart signals at subgroup T. So that is process will be in out of control situation. So this point at which at subgroup point T, the process engineer must initiate a search for the special cause of variation. So we denote tau, that is the last subgroup from the in control processes. So here will two parts of the process. That is first one contains x bar 1 to x bar tau are the subgroup averages from the in control processes, while x bar when change takes place in the processes, then x bar tau plus 1 to xt are the subgroup averages when the process parameter changed. So here now the process step model is considered. So we consider the maximum likelihood estimator of the changed process level parameter. So we consider a technique to detecting this change point using the PDF of the sample mean of AR1 process. So we consider the MLE of change point tau as tau hat. So the probability density function of sample mean of AR1 process is given by this equation f of x bar. Then we take its likelihood function, which is given by the L tau mu1 x bar by this equation. Then by taking the log likelihood function apart from these constants. So here we consider the first observations are coming from the in control mean. So this xi minus mu naught. Here we consider this in control mean parameter, and the second next observations after process changed. So these observations having the changed process mean, that is mu1. So after simplifying this, we will get equation 3. So in this equation 3, this term, so it follows that the value of tau which maximizes the log likelihood function. So this tau hat is equals to max t minus tau mu1 hat minus tau minus mu naught bracket square. So this is the value of tau in the range 1 less than tau less than t, which maximizes equation, where t is the control chart gives the out of control signal. So performance of this estimator. So we conducted simulation study here to check how this change point estimator approach to identify the time of the change in the process. So we used the X bar chart with observations are observed from AR1 model, and we consider the subgroup of size n is equals to 4. So in control average run length of this for this chart is 370, which is equals to the conventional Sheward X bar chart. So the change in the process is simulated at the point tau is equals to 100. So the first 100 observations will have the in control parameter value, that is mu naught equals to 0 and sigma naught equal to 1. And the subsequent subgroup have the changed value delta and standard deviation 1 until the AR1 X bar control chart gives out of control signal. And this is not a false alarm. That is, the process actually gets out of control. So at this point, we applied our estimator and computed a tau hat, and this procedure is repeated 10,000 times for each value of delta and for different value of phi in steps of size 0.2. So the average of the estimates obtained using the estimator from the 10,000 simulation run is computed with their standard errors. So simulation results are tabulated here. So here expectation T is equals to 100 plus ARL. That we have taken the 100 in control observations and plus ARL. That means when the control chart gives the out of control signal. So AR1 X bar control chart for the delta is equals to 0.5 when shift of 0.5 is considered in the level parameter, and for the value of points value of phi is equals to 0, so it is equals to 2.254, and for that the estimator signals at 104. So we have considered tau is equals to 100. So for similarly for phi minus 0.6 to 0.6, we can see that the expectation T is greater than the tau hat bar. So the before control chart signals, our estimator detects the change in the process. So similarly for delta is equals to 1, we can see. So expectation T for minus 0.6 and for delta is equals to 1 is 211, and the change point is detected at 99.99 subgroup. So,
Madam, can you please conclude?
Yes, just 1 minute. So here we can tabulated precision of estimator for delta. So this is the, we can examine it by probability that tau hat is within m observations of the actual change point. So here exactly change point detected at 100. These probabilities are summarized here. So conclusion. So knowing the time of process change helps search for the special cause, so they can improve the quality of process more quickly. So we showed that the proposed estimator provides a useful and better alternative to using the time of the signal from the control chart. So the results of the simulation study shows that the proposed estimator is effectively works in detecting the true time of the change of the process change. So these are some references, and thank you.
Thank you so much, ma'am. Okay, now I request Dr. Suvarna Patil to present her paper, and the title of the paper is Tolerance Intervals for the Alpha Power Rayleigh Distribution as an Example of Alpha Power Transformation Method. Dr. Suvarna Patil. Madam. Suvarna ma'am. Madam, you are not audible. Yes, ma'am, you are audible.
Good afternoon, ma'am. Actually, I'm joining from my laptop.
Yes, ma'am.
So please give me permission of my laptop. Yuvraj Patil's screen.
Yes, ma'am. It is permitted. You can go ahead. Your screen is visible, madam. Madam, you can go ahead.
Good afternoon, everybody. My screen is visible, madam?
Yes, madam, you can go ahead. Your screen is visible.
Okay. My topic is tolerance intervals for the alpha power Relic distribution as an example of alpha power transformation method. First, I explain abstract. In this paper, we consider the tolerance intervals for the alpha power Relic distribution as an example of the alpha power transformation method on the lines of Mahadvi and Kundu. We obtain the maximum likelihood estimates of the unknown parameters. Yes. We propose beta expectation tolerance interval and beta content 1 minus gamma level tolerance interval for alpha power Relic distribution when scale parameter is unknown. We also propose generalized tolerance interval based on generalized variable approach for alpha power Relic distribution when shape parameter is known. Performance of tolerance intervals is investigated via simulation study. Here we use alpha power transformation method, generalized tolerance interval, beta expectation tolerance interval, beta content 1 minus gamma level tolerance interval, and also maximum likelihood estimator. Some introductory part is that the main objective of this work are to draw statistical inference on the unknown parameters of newly defined distribution, alpha power Relic distribution, by using alpha power transformation method and determination of different tolerance intervals for this distribution. Mahadvi and Kundu in 2016 defined alpha power transformation method to design new distribution. In this work, we consider alpha power transformation method and define new distribution, alpha power Relic distribution, as follows. Okay. This is alpha power transform density PDF of alpha power transformation method. The random variable y is said to have a 2-parameter alpha power Relic distribution, which is denoted by APR alpha lambda with the shape parameter and scale parameter. Here is the PDF 1.1. The CDF of y becomes, which is given in equation 1.2. Here we obtain the MLE of the scale parameter based on complete data. We provide the MLE for the sake of clarity as we need to estimate different tolerance intervals. The MLE cannot be obtained in closed form. We use Newton-Raphson method to compute maximum likelihood estimate. Next, we consider tolerance interval for alpha power Relic distribution. In general, the term tolerance interval is an interval determined from observed values of a random sample for the purpose of drawing inference about the proportion of distribution contained in that interval. There are two types of tolerance intervals, namely beta expectation tolerance interval and beta content 1 minus gamma coverage tolerance interval. Here beta expectation tolerance interval is given, beta content 1 minus gamma coverage tolerance interval is given. In section 2, we explain estimation of parameters. We use here maximum likelihood estimation. In next section, we give here larger sample tolerance interval. Here we obtain beta expectation tolerance interval for alpha power Relic distribution, which is an example of alpha power transformation method with a scale parameter lambda. This is let x beta lambda with the lower quantile of order beta of the distribution function. Here lambda scale parameter is unknown, hence we replace it by its MLE. Also we obtain modified MLE. Scale parameter is unknown, we replace it by MLE and also modified MLE. In 3.1, we give approximate upper beta expectation tolerance interval for our alpha power Relic distribution. We approximate using Hartwood, which is used in 1984, expectation of our beta expectation tolerance interval. Here we replace MLE by modified MLE and also obtain beta expectation tolerance interval for alpha power Relic distribution based on modified MLE. Simulation and approximate values of expected coverage using MLE and modified MLE have been reported in following tables. for different values of n, beta, and alpha. In the simulation study, we generate n observations on alpha power Relic distribution with a scale parameter lambda. Using Newton-Raphson method, we obtain MLE, and using Tiku's approach, we obtain modified MLE based on the generated n observations. We repeat this procedure for both intervals for n is equal to 3 to up to 50. Figures in the first row are based on MLE, and figures in the second row are based on modified MLE. This is table number 1.1, simulated mean and estimated expectation of the coverage of approximate beta expectation tolerance interval for alpha power Relic distribution. Here we put alpha is equal to 2, and for various values of scale parameter lambda, we obtain here simulated mean and estimated expectation for n is equal to 3 to up to 50. And here we consider in next table alpha is equal to 3, and similar results we obtain here, which are given in this table. From this table, we observe that simulated mean of the coverage for small sample size is below nominal level. Estimated expectation and simulated mean of the coverage increase as sample size and increase. The estimated expectation of the coverage of the approximate beta expectation tolerance interval shows satisfactory result for large n. Estimated expectation and simulated mean of the coverage increase as the shape parameter alpha increases. Then next we find here beta content 1 minus gamma coverage tolerance interval for our this newly defined distribution, alpha power Relic distribution. Here we obtain upper tolerance limit in this equation 3.7. Here D depends on the unknown parameter lambda. The performance of this also tolerance interval is judged by simulation study in next session. Then we use here generalized tolerance interval. The concept of generalized confidence interval is due to Virhandi in 1993. By using this concept, we find out generalized pivotal quantity, and using this approach, here we obtain generalized tolerance interval. The problem of computing one-sided tolerance limit reduces to that of computing a one-sided confidence limit. So here, using our regular confidence interval, here we use a generalized confidence interval, and we obtain beta 1 minus gamma upper tolerance limit, which is simply and 1 minus gamma upper confidence limit for the 100 beta percentile of the population. This is the upper tolerance limit for our alpha power Relic distribution, which is simply 101 minus gamma percent upper confidence limit for this one. We use here GB approach. For GB approach, we first define generalized pivotal quantity. Using this generalized pivotal quantity, we obtain generalized tolerance interval, and which is obtained by using this algorithm. Here I explain this, I given this algorithm, and then this is simulation results. Coverage probabilities of tolerance interval for alpha power Relic distribution. Here we take beta is equal to 0.90, 0.90 so on, and gamma also 0.90, 0.95. Coverage probabilities, here we find coverage tolerance intervals for various values of n is equal to 3 to 50. We have determined here. These are some simulation results. We observe from these tables generalized tolerance interval performs satisfactory as compared to beta content 1 minus gamma level tolerance interval. The coverage of beta content 1 minus gamma level tolerance interval decreases as a sample size n decreases. Simulated level of beta content 1 minus gamma level upper tolerance interval shows good performance for large sample size, while it is below nominal level in small sample size. For generalized variable approach, it is close to nominal level for all sample size. As
Can you
such,
please conclude?
Significant effect of increase in K on performance of tolerance intervals using GB approach. The number of units in parallel system. Performance of generalized tolerance interval and beta content 1 minus gamma level upper tolerance interval occurs in same manner, whether they are computed by using MLE or modified MLE. In this section, we obtain tolerance interval for alpha power Relic distribution. Here numerical and simulation study is given. These are conclusions. In this work, we have made statistical inference on the unknown parameters of alpha power Relic distribution as an example of alpha power transformation method. The performance of the proposed estimators is found to be satisfactory even when the sample size is moderate. We have obtained a beta expectation tolerance interval, beta contained gamma level tolerance interval. Also, we have obtained a generalized tolerance interval based on generalized variable approach. We have seen the performance of the tolerance interval based on large sample approach needs large sample size for its performance at the desired level, while generalized tolerance interval is satisfactory even when the sample size is small. These are some references.
Thank you, madam.
Thank you, madam.
Professor Mk Patil, sir. So, on behalf of KLE's PC Jabin Science College, Department of Statistics, and the organizing committee, I extend my deep sense of gratitude to Professor Mk Patil, and I also thank all the research scholars for your knowledgeable presentations. Thank you. We'll be having a short lunch break, and we'll be back at sharp 2:40. Thank you so much. Please join with the same ID. Thank you.
Baile. Huh? Bande.
Okay. Very good afternoon to one and all. Once again, I welcome you all to this national conference. It's my pleasure to welcome the chairperson of this session, Dr. Mk Patil, Associate Professor, Karnataka Arts College, Dharwad. Dr. Mahadevappa N. Megeri completed his MSc, PhD in statistics. He has done number of research projects and has 29 years of teaching experience. He has attended about 30 national and international conferences and is an active life member of many organizations. With this short introduction, I welcome Dr. Mk Megeri, sir. I welcome you, sir. I would also like to welcome the invited speaker of this session, Dr. P.G. Dikshit, Professor, Department of Statistics, Modern College of Arts, Science and Commerce College, Shivajinagar, Pune. I welcome you, sir. Now, I request Dr. Rudraswamy NG, Head of Department Mathematics, to introduce the invited speaker of this session.
So, I take privilege in introducing the speaker of this session, Dr. P.G. Patil, P.G. Dikshit, Professor, Head of the Department and Vice Principal of Modern College of Arts, Science and Commerce, Shivajinagar, Pune. Sir has a vast experience of 41 years of teaching in UG and PG studies. He has been a resource person in a number of workshops, seminars, refresher courses, and other academic pursuits in and outside Maharashtra. He has undertaken several research projects and conducted national and state level seminars. He has published 103 textbooks for various classes of BSc, BCom, BBA, BCA, and biotechnology. Even he has authored 2 research articles in peer-reviewed international journals. Sir has been a member of various academic bodies. Important among them are member of Board of Studies in Statistics, University of Pune for 15 years. He was chairman in the Board of Studies in Statistics for 5 years. He was also co-opted as member of Board of Studies in Statistics at Bharati Vidyapit Pune, Solapur University Solapur, Swami Ramanand Tirth University Nanded, Dr. Baba Saheb Ambedkar Marathawad University Aurangabad, KG Somaya Autonomous College Mumbai, and RLS College Belgaum. He is a member of Textbook Rating Committee for Class 10 in Mathematics at Maharashtra State SSC Board, Pune. He was a member of Academic Council, University of Pune for 5 years. Member of BOE Reforms Committee for 5 years. Along with the academic, he is actively involved in administrative and social works. Presently, he is the Deputy Secretary of Progressive Education Society, Shivajinagar, Pune, and Vice Principal. Sir has been associated with Student Welfare Association, and he was a member of Board of Trustees of Schizophrenia Awareness Association, Pune. For his contribution in academic and administration, he was recognized as the Best NSS Officer Award at university level in 1995. He is a recipient of Best Teacher Award by Municipal Corporation, Pune in the year 2000. He has received Dr. Manibhai Best Teacher Award on Gandhi Jayanti in the year 2009. With this introduction and with the permission of Jay, I would now invite Professor P.G. Dikshit for his invited talk. Thank you. Now I request Chairman to continue this session.
Hello. Hello. I'm audible?
Yes, sir. Yes, sir. Yes.
Yes. So, welcome to the second session of the third invited lecture. I welcome Dr. P.G. Dikshit and Professor and Head of the Department of Modern College, Pune. So, I request Professor Dikshit to start the lectures. Dikshit ji? Dikshit?
Sir, you are on mute.
Unmute.
Okay. Okay. Am I audible now?
Yes, sir.
Hello. Yes. Thanks for nice introduction. with thanks to chairman of the session, Megiri, and all participants. Thanks for nice introduction. I have chosen a topic today, applications of simulation, and it is in concurrence with the theme of the seminar or conference. Okay, so let me start presenting. Yes, is it visible?
Yes, sir, it is visible.
Okay, the screen is visible.
Yes, sir.
Just a minute, I am not able to read it.
Yes, sir.
Okay, anyway, I'll read from my hard copy. You can see it. Okay. So statistical applications of simulation. So first of all, let me tell you what simulation is, just to begin, although you know what it is. So it is a method of imitating a real system with artificial data using computer which closely represents the actual working of real system under the given set of conditions. There are a lot of applications in the present era of IT, and this one, yeah, you can say artificial intelligence. Okay. So there are various fields where the simulation is used. In manufacturing, with the help of robots, there are so many things are done. And then in working of various tools and machines, manufacturing is used. Air pilot training is done with the help of simulation. Even surgeries are done with a simulated hand, with a artificial hand. Vehicle crash test and in automobile industry is conducted. It is nothing but a sort of simulation. In interior designing, a lot of simulation is done. In beauty parlors also, a lot of simulation is done. In interior designing, without actually designing or without actually decorating the house, the interior designer places sofa at some place, then table at other place, and then he makes certain arrangements on screen itself, and that is nothing but a simulation, you can say. In beauty parlor also, which type of haircut will suit to a particular lady, that can, without cutting actual hair, one can decide. So in beauty parlor, there are a lot of places where the simulation is done. Simulation in research, space research and explosives and missiles heavily make use of simulations. In statistics also, we use simulation at several places. And one of the place where I will be discussing 2 or 3 places where simulation is done. In testing of hypothesis, there are several situations where one can go for simulations. Then another important area of statistics is statistical process control. I saw there are a lot of speakers who are talking on control charts, where this working of control chart or efficiency of control chart, all these things are determined with the help of simulated results, because every time the things cannot be obtained mathematically, not tractable. Similarly, evaluation of definite integrals. There are so many definite integrals we evaluate. For example, normal probability we obtain, that is nothing but a definite integral, in which we do not get a explicit solution for that, and we do see the statistical table. And so is the thing that about incomplete gamma, incomplete beta, and similarly bivariate normal distribution. We never ask a question that find by a probability that x and y belong to a certain region when x and y are bivariate normal distributed, because the tables are not available, and the integral, double integral, that definite integral, that is not tractable, mathematically tractable. So we avoid asking such questions, and we avoid teaching also. And there are these things definitely some or the other time you need to do either in research or at some projects or somewhere, and you definitely require to talk about or to determine such integrals. So evaluation of such integrals is possible with the help of simulation. So let me explain this idea of simulation with the help of this example. So here you will see, yes, do you see this figure? Hello? Hello? Do you see the figure in transparency? Hello? Hello, am I audible? Hello?
Yes, sir, you are audible.
And this figure is seen?
Yes, sir.
Okay. So in this figure, you will see this is a simple application of simulation. While introducing simulation, we take help of this figure, or I generally take this example to explain what simulation is and how it can be used in estimation of integrals. Okay. So in this, you see this shaded area is a irregular shape, maybe a lake or maybe a plot, and we want to find out area of this plot. So what can be done? We can find a rectangle in which this plot or this lake is inscribed. So a rectangle which is outside this. So consider an example which is sort of simulation. Suppose I have 1,000 pebbles in my hand, and I make an arrangement to throw these 1,000 pebbles in this area, in this rectangle. Okay, how I will drop, that is different thing. Suppose I have a helicopter and I can throw these pebbles in uniform manner in this area, in this rectangular area. And I know that suppose out of these 1,000 pebbles, 760 pebbles lie in fall in the lake, and the total 1,000 pebbles I have considered. Okay, so you know here, since the pebbles are uniformly spread, uniformly thrown, so the pebbles in that particular area will be proportional to the area. Okay, so area plot divided by the ratio area of plot to area of rectangle, that will be approximately equal to the number of pebbles which fall in that area. So suppose 760 pebbles fall in area of plot or area of lake, and 1,000 pebbles are thrown in total in that rectangular area. So area plot upon area of rectangle is 760 divided by 1,000, and therefore area plot, estimate of area plot will be 0.76 into area of rectangle. Okay, so this is also called as a Monte Carlo simulation. There is a small difference in simulation, Monte Carlo simulation and the other simulations. In Monte Carlo simulation, here the area of plot we are obtaining. Area plot is a fixed quantity. It is not a variable. So when you estimate a fixed quantity, this simulation or this technique is called as a Monte Carlo simulation. And if that quantity is a variable and you are estimating it, then it is called as simulation, you can say, or our usual simulation. So this is, with this difference, let me go ahead. And now how this can be made, how this can be used to obtain the area under the curve, okay, or the integral. Okay, see this integral, this is a integral from a to b, definite integral fx dx, and now this integral is nothing but, geometrically speaking, this integral is nothing but area under the curve. Okay, now in earlier example I had a irregular shape area, and that I have covered by boundary which is regular one, or which is a rectangle. Okay, similarly here I have to find the area of this particular part, area under the curve. So I inscribe this area in a rectangular shape. Okay, so I take rectangle which is slightly larger than this area. Okay, so I know that integral a to b, this a is nothing but the rectangle, this ordinate at this particular place, and b is nothing but ordinate at this particular place, and I take h as the height of this rectangle. So I know the area of rectangle, length into width. The length will be b minus a, and height will be h. So b minus a into h will be the total area of rectangle. So like earlier rectangle. And now this irregular shape is nothing but the area under the curve, or the integral. So I have to now throw tables in it. Now statistically, how to throw pebbles in it? So that we can do with the help of random numbers. Okay, so I draw random numbers between, I draw a pair of random numbers, that is x value will lie between a and b, and y value will lie between 0 and h, because x will denote, or x will be nothing but the base of the rectangle, and y will be nothing but the height of the rectangle. So I take two random numbers, that means I take 2 points, okay, in xy coordinate, like that. So these xy coordinates are, I have chosen randomly, which will fall in this rectangular area. Now my value of y that I have chosen as a random variable, whether it lies below, it lies definitely in the lies in the rectangle, but whether that particular value of y is below the curve, y equal to fx, or it is above, that can be seen by just comparing the value of function at that point, fx. Okay, so fx will be compared with y, and I will count how many pebbles will lie in this area. That means how many random numbers or how many random pairs will lie below fx, and how many pairs will be above fx. So I definitely know the proportion of the number of random numbers which are below fx, and that proportion is nothing but, that will be nothing but a representation of the area of this rectangle, the area of this area under the curve. So the simulation steps to evaluate the integral. So evaluation of integral is nothing but evaluation of irregular shape area. Now here only one side is irregular, remaining 3 sides are regular. So that one side is inscribed into a bigger rectangle, and we can proceed further. So what will be the procedure? Draw n pairs of random numbers x and y, I equal to 1 to n, where xi between a and b, and y will be between 0 and h. Y stands for height. Okay, then I find fxi for the above random number xi, and observe whether y is less than fxi. If y is less than fxi, my pebble is in the shaded region. Okay, so instead of table I am using the random numbers. Okay, so I count how many pebbles are here. So total pebbles I have thrown, or total random numbers are n, out of which m will be in this area. So m will be below the curve, y equal to fx. So the area of this area under the curve will be proportional to m upon n, and therefore this area of rectangle multiplied by this p proportion. Okay, so that will be the value of rectangle. So in this manner I can evaluate the rectangle. The same idea can be extended for double integrals and multiple integrals. Now, one can definitely ask a question. Finding area of the rectangle, one can use trapezoidal rule or Simpson's rule or something of that sort. Okay, definitely it is there. That can be done. And moreover, when you go for double integral, these rules become complicated. And when you go for multiple integrals, these rules are very complicated. And however, this particular method of simulation, even evaluating double integrals and multiple integrals, that is very efficient one. Okay, that is what given in the book by, I have a book on simulation by Subramaniam or someone. I do not remember the name, but he explains that area under the simulation of multiple integral with the help of that will be definitely more useful or more superior, or you can say more easy and implementable if you use simulation. Okay, so instead of double integral, you go for multiple integral, and then you will find how difficult that the method is. So in double integral, just I will generalize this to double integral. Okay, so I could not draw the three-dimensional diagram, but you can imagine a double integral is nothing but imagine a ice cream cone. Okay, you want to find the area of ice cream cone, and what I am going to do, I am going to put that ice cream cone in a box. So that box will be nothing but generalization of rectangle, and area of cone will be nothing but generalization of three-dimensional plot. Okay, instead of plot, it will be three-dimensional. So that surface. Now, however, here in double integrals, what happens? The two sides are x and y axis. Two sides are okay. They are regular, but the surface, the z axis, that surface is uneven, or it is not in proper geometrical shape, and we want to find area under this surface, below the surface. And then what can be done? Here you have to generalize it to three-dimensional case. It is double integral. So instead of drawing a pair of random numbers, here you will find, or here you will draw n triples of random numbers, x, y, z. So x will lie between a and b, which is nothing but the limits. Okay, limit of outer integral is a to b, that is x. Limit of inner integral is from c to d, so y is between c to d, and z is nothing but the height. Okay, so that will be between 0 to h. Suppose h is the height of the box, or you can say it is a cube. So you are inscribing this area in this cube. So you find these three random numbers, and you find the value of function fxy for that particular pair, that is xi, y, and you observe whether that z value, your random variable z, is less than fx or less than fy, less than fxy or greater than fxy, and you can count how many random numbers fall in that ice cream scoop or ice cream cone, and how many fall outside. But of course, they fall in the area, the cube. Okay, so counting that number, suppose it is m, so you have drawn n pairs, out of which m pairs fall in that ice cream cone. Okay, so the proportion of the volume of that ice cream cone will be proportional to m upon n. And now area of the total
Prakash sir, you're on mute. Okay, sir.
Am I audible?
Yes, sir.
Okay. So that will be approximately So this double integral will be nothing but approximately b minus a multiplied by d minus c multiplied by h and p. This p part, that is p is m by n, that is simulated. Okay, so this is how double integrals can be evaluated. Now, you know, normal distribution we always use and find the probability, normal probability. How do you obtain normal probability? We see normal statistical table. Okay, so area under the normal probability integral we find, and that cannot be obtained just like we solve our usual integrals. And that is nothing but the table is made available. Suppose table is not there, then how to proceed further? So the simple way is there. Suppose I want to find probability that x is less than equal to 1 when x is normal, standard normal. So simulation process can be applied. So I am explaining this because this can be implementable to the other integrals like gamma, beta, etc. So what you can do, you draw a sample of size n from normal 0, 1, count the number of x's below 1. That means you find the proportion of the numbers which are below 1. Suppose n random numbers you draw, out of which m fall below 1. So m upon n will be nothing but approximately the proportion. It is proportion of the number of observations less than 1. And this proportion converges to the probability x less than 1. You know, this convergence in probability takes place. So this m by n is nothing but an estimate, is a consistent estimator of this probability. And therefore, this probability x less than equal to n is m by n approximately, is a consistent estimate. So this is how you can obtain, you can evaluate the other integrals, beta, gamma, incomplete beta more specifically. So let me come to that part. Okay, now is it visible? Hello?
Yes, sir, it is visible.
Where it is visible, I cannot locate. Anyway.
Applications of simulations, right?
Oh, yeah, true. But I cannot see on my screen. Okay. So anyway, in my hand, I have a copy and I will explain.
Okay.
So there are different methods of simulation. This is a long lecture I have prepared, but I will not explain each and everything over here. Just it will take the complete view of all these things that I have decided to discuss, but I am not going to discuss everything here. So different methods of simulations are there. That part I will skip. Then linear congruential generator method is generally very much famous, and the choice of ABC, there will be a separate lecture on choice of these ABC, and how the random numbers are really random, pseudo random numbers. That will be also another topic of, and there are so many statistical tests developed for this purpose, and that will also be a different topic of seminar. So here, what I would like to discuss or tell is to evaluate different integrals. Okay, so I have listed here 6 different integrals. The first one is 0 to infinity e raised to minus x to the power 3.7 dx. Okay, this is incomplete gamma integral, and this is nothing but gamma 4.7. We know gamma 4, we know gamma 5, but gamma 4.7 how to obtain? And many times we require in teaching and in solving examples, gamma 4.7 how to obtain. So that is really a problem. So gamma 4.7 is nothing but an integral, gamma integral 0 to infinity e raised to minus x to the power 3.7. So here you can evaluate this integral using simulation that I will explain later. Just me explain these 6 examples, 6 integrals, different integrals. The second integral is 0 to infinity e raised to minus x into sin x dx. Okay, I have to evaluate this integral. Okay, so that can be done. The next integral is incomplete gamma. This was a complete gamma, 0 to infinity. This is also a complete gamma. Now this is 5 to infinity e raised to minus x cube dx. Okay. This is nothing but a incomplete gamma, and the incomplete gamma table you have to see. That may not be readily available. And the next is find the value of 1 to infinity e raised to minus x square by 2 square, that is 4. And this is nothing but a you can say the integral from normal distribution. And then this is incomplete beta. Okay. Sorry, it is beta 4.6 and beta 3.3. How to obtain this beta? You know beta mn, when mn and n are integers, you can easily find, but these values are required many times. Okay. Similarly, a double integral, bivariate normal integral, probability that x is lying between 0, 1 and y is lying between 1 and 2. This probability you have to find out. So how to obtain this? So a simulation technique can use. Now this simulation technique, what is the base for this simulation? This simulation is based on a weak law of large numbers. What does this statement says? That the statement is that when you take x1, x2, xn, a sequence of independent and identically distributed random variables with finite mean mu and variance sigma square, then x bar converges to mu in probability as n tends to infinity. Making use of this particular theorem, weak law of large number, one can evaluate. Now let us evaluate this integral gamma 4.7. So gamma 4.7, okay, see. Can it be scrolled? Is it scrolled? Hello?
Sir, you have to scroll, sir.
Yeah, that I am not getting how to scroll. How one can scroll it? Earlier I have converted it into the, okay.
Sir, can you stop sharing the screen and try to share it again, sir?
Okay, okay. Yes, now can you see?
Yes, sir.
Yes, okay. So this is nice thing that I have prepared, but okay. So this is 4.7, gamma 4.7 is nothing but integral from 0 to infinity, e raised to minus x and x to the power 3.7. So this integral can be viewed as expected value of x to the power 3.7. That means it is nothing but 3.7th order raw moment. Okay, so this raw moment I have to estimate. Okay, so the procedure in this case will be, so it is nothing but a raw moment when x is exponentially distributed. So this gamma 4.7 or this integral, this amounts to what? This amounts to finding this integral, or finding this integral is nothing but finding expectation of x to the power 3.7 when x is exponential. So what I'll do, I'll take a random sample from exponential. I will find out x to the power 3.7 and I will find a raw moment. So raw moments are estimates, consistent estimators of population moment, that I know. So using this particular result, I simulate. So the procedure is simulate x1, x2, xn, n observations from exponential distribution with mean 1. Okay, it can be done in simple manner. Okay, this we know, everybody knows how to draw a random sample from xi. Instead of saying random sample, Prasad sir always says that you should use particular word simulation. Okay, so simulate and then compute Sn, that is 1 upon n x to the power 3.7. So it is nothing but 3.7th order raw moment of order 3.7 used from sample, and this will be an estimator of population value. Okay, so this Sn is nothing but estimate of 4.7. Okay, so this is Monte Carlo simulation to evaluate this first integral. Now next integral is say e raised to minus x into sin x dx. Okay, this integral again is complicated, and if it is required, then you can find x1, x2, xn, n observations from exponential with mean 1. It can be done in simple manner as usual. Then compute Sn, that is 1 upon n expectation summation 1 to n sin xi, where xi's are nothing but exponential random variables. Okay, so now for large n, this Sn is nothing but a consistent estimator of the integral e raised to minus x sin x. So these were complete integrals, and therefore there was no problem. No, there was not a problem. So it is nothing but a interpretation. So how we have interpreted the integral, and we have obtained its consistent estimator, and accordingly we have obtained. Next integral is find the value of 5 to infinity e raised to minus x to the power 3 dx. So this is incomplete gamma, and obtaining this may be very difficult. Of course, in this case, it may be a little simple because you can view it as a gamma distribution, probability of gamma distribution. This gamma can be converted to chi square because this is integer, x to the power 3. 3 is integer. But when 3 is not integer, there is a problem. Okay. So in this case, you can see, however, you can find it as, this is nothing but the above integral can be viewed as probability x greater than 1 when x is gamma. So you simulate from gamma and find the proportion, how many of them are greater than 5. How to simulate from gamma? Gamma can be viewed as sum of exponential variables, 3, y1, y2, y3. So you draw n triples from exponential, y1, y2, y3, add up them, and how many triples out of n, how many triples have sum more than 5. So that proportion is nothing but estimate of the probability. So m upon n, this will converge in distribution to the probability. So simulate n triples, compute xi for each, then count the number of xi's greater than 5, let it be m. So this p is equal to m upon n. This p is proportion of simulated values of x which are greater than equal to 5, and for large n, p converges to this probability in probability. Okay, so this is nothing but an estimate. So we are estimating using simulation or using random sample. And here this is, this is usual standard normal probability x greater than 1, and there are several ways to obtain it. Okay, simulation from normal distribution, Box-Muller transformation is there, and apart from that there are so many others also. Okay, so simulate x1, x2, xn from standard normal distribution. That is one thing using Box-Muller, and you can find this proportion. Okay, count the number of xi's which are greater than 5. If it is m, then m upon n, this proportion is nothing but the value of the integral. So this is how you can obtain the integral. There is another way to do it. This is very simple and elegant way to generate observation from normal 0, 1. If Box-Muller is not known to us, suppose in that case, what you can do is, x1, x2, xn is sample of size m from uniform 0, 1. And z is equal to, say, standardized uniform, that is sigma xi minus its mean is m by 2. Mean of xi is half. So mean of this summation is m by 2. And variance is 1 upon 12. So variance of all this sum, this entire sum is m by 12. So due to central limit theorem, this z tends to normal 0, 1 as m tends to infinity. And for m equal to 12, let us get. So this can be made simpler. If you take m equal to 12, then this will be 6 and this will be 1. So simply z equal to summation xi minus 6. What this xi is? These xi's are nothing but addition of 12 uniform random variables. Okay, so to generate one observation from normal, you take sample of size 12 from uniform 0, 1, subtract 6. That's all. And this z will be a single observation from normal distribution. So repeat this procedure n times and then find out this proportion, and you can find the probability. Okay, and this is beta integral. See, incomplete beta or complete beta. This is complete beta. 0 to 1, 3 raised to x raised to 3.6 and 1 minus x raised to 2.3. So the above integral I can be viewed as a beta function. So it is nothing but expected value of x to the power 3.6 and 1 minus x to the power 2.3. So this is beta 4.6 and 3.3 when x follows uniform. Okay, here you can consider, here there is a PDF of normal uniform 0, 1. You can consider this as PDF of uniform 0, 1. 1 is not there, so you can consider 1, and therefore this can be viewed as this x to the power expectation, this particular moment. Okay, this is a raw moment from uniform distribution, and you can simulate from uniform distribution. Simulate n observations from uniform distribution on 0, 1. Compute this Sn. Okay, exactly this expectation. This is population value and corresponding sample value is this. And then for large n, this Sn will converge to beta. Okay, so this is how beta simulation can be done. Okay, and then the question comes, finding double integral or finding probability from bivariate normal. I do not know how many of the participants have obtained this probability. Okay, so because this was a problem when we asked our PG students to calculate this probability, there is no statistical table available for bivariate normal. When x and y are independent, there is no problem, you can find easily. But when it is not, when they are correlated, x and y, then it becomes very difficult. And again, the procedure is what? You simulate from bivariate normal and find proportion, how many lie in this category. And then that proportion is nothing but estimate of the probability. So what we need to do is simulate n pairs of observations from bivariate normal. Okay, and how to do it? There is a result. If x and y follows bivariate 0011 row, 0011 row, why I have chosen? Because if it is mu1, mu2, sigma 1, sigma 2, then you can convert this. Okay, x minus mu upon sigma and y upon mu2 minus sigma 2 divided by sigma 2. That gives bivariate normal 0011 row. So without loss of generality, I have taken x and y bivariate normal 0011 sigma row. In that case, x plus y and x minus y are independent normal 0, 2, 1 plus row and independent normal 0, 2, 1 minus row. That means x plus y will be normal with mean 0 and variance this one. X minus y is also normal when mean is 0 and variance is this. And then you can find the value of u and v. So u is x plus y upon this quantity. So I have standardized it. V is standardized. So when you know x and y from bivariate normal 011 row, I get a pair u and v which are independent, identically distributed normal 01. So take a pair from bivariate and I get a pair from bivariate but independent random variables x and y. So x and y can be obtained in this manner. So that means u and v can be obtained and u and v can be converted into x and y in this manner. So drawing n random sample of n pairs of random variables from bivariate normal is possible in this manner. So the procedure is explained here. Draw a simple random sample ui vi I equal to 1 to n from normal 0, 1. Then transform them to bivariate normal using this transformation given in 1. Then count the number of pairs such that xi is between 0, 1 and y is between 1, 2. Suppose that proportion, that number is p, that number is m. So p is m upon n, and this p is proportion of simulated variables, and therefore this p converges to the desired probability. So this is how you can go ahead. Okay. So let me, how much time I have, madam? Hello.
Yes,
hello,
sir.
How much time I have?
Sir, please, you can conclude, sir.
Okay, this just I'll show this and conclude. So application of simulation in testing of hypothesis. This is, suppose I want to test normal mu equal to 0 against mu equal to 1 sigma square. Then most powerful test is there, summation xi greater than c. When mu is greater than mu naught, and for a specified value of alpha, we can find the value of c. Now let me make this hypothesis as h naught mu equal to 0 and when sigma squared equal to 1 versus mu equal to 0 and sigma squared equal to 9. That means standard normal versus normal 1 and sigma squared. I have to see, this is 1. No, sorry, make it 1. Okay. Then most powerful test is of this type. 4 summation xi square plus summation xi greater than c. How to find the value of c? To find the value of c, I require the probability distribution of 4 summation xi square plus xi. This is very difficult. Okay. If 4xi square is there, I can find out. If summation xi is there, I can find out the distribution. Xi squares, I can go to chi-square or non-central chi-squares, and summation xi is sum of normals, so I can go ahead. But a chi-square, non-central chi-square and normal mixture, how to find the probability distribution is very difficult, and simulation is one of the way. So what to do, how to obtain the value of C? Let us see here. The procedure is C is equal to find C when alpha is 0.05. So we simulate M. M is suitable number. Okay, you can take, I have taken 100 in this case. I have simulated this. Okay. So simulate M set of x1, x2, xn's from normal 0, 1 and evaluate T. What is that T? Evaluate this. For each sample, you can find this, and then you can arrange all these T's in increasing order, and alpha is equal to 5%. So select the top 5%. Okay. So we find C such that top 5% T's are exceeding C. So simulation from, and therefore simulation from 100 normal 0, 1 gave most powerful test that the value of C came out to be 77.9007 at 5% level of significance. And what will be its power? The power is 1. Okay, that I will show here. Just a minute. See, these are simulation results. See, under H1, let me take under H0 first. Okay. Under H0, that is standard normal 0, normal distribution. These are x1, x2, x10 observations, sample of size 10. Then this is sum of square. This is the value of T. So all these T values are obtained for 100 observations. Okay. Then those are arranged in increasing order. And now I want a 5% value. So among these, top 5% will exceed this particular value, that is 77.9. So my C is nothing but 77.9. And with this C, what will be the power? So the power calculations, okay, here I have done. So under H1, that is normal 0, instead of normal, under H1, normal mean 1 and sigma squared 9. So these are 10 observations, 10 by 100. So these are simulated values. This is sum of the observations, this is sum of squares, and this is T value, test statistic. And then all those are ranked here. And you see probability that, or the proportion of T value exceeding 77.3, something 77.09. So here all the values are above that. And therefore power, achieved power is 1. Okay. So in this manner, this problem, otherwise it is very impossible to solve. Okay. For sample of size 1, the problem is slightly easier, because using NP lemma, you get this critical region to be modulus x plus 1 by 8 greater than C. Okay, and the value of C you have to obtain, but this value of C cannot be that obtained so easily. Again, here you need to take the help of simulation. Okay, and this simulated value that gives C equal to 1.76 at 5% level of significance. The actual level of significance comes out to be, that can be calculated here, that comes out to be 0.07, which is very close to 5%. With the help of, with the target value 5%, we have obtained C value. This exact C value cannot be obtained. It's so difficult. And then power can be calculated. Power can be exactly obtained when one's value of C is there. So power is 57%. So another problem is here, just I will briefly tell you, I have not solved it, but suppose there is a single observation and we want to decide whether it is coming from standard normal or it is coming from Laplace. That we do not know. And the test using simple Newman-Pearson lemma, that also becomes very complicated. That is, so x plus 1, when x is positive, you get another rule. And when x is negative, you get a different rule. And these values of K1 and K2, when x is positive and x is negative, calculations is very difficult. Because, you know, this K1 and K2, so again, a simulation technique may help here. Okay, so this is how you can go ahead. And then in control charts, a lot of people have talked about control charts and ARL calculations. particularly in Kusum chart and EWMA chart or any chart on further. ARL calculation, ARL formula cannot be obtained. So ARL calculations are simply you have to do with the help of simulation. So there are lot of places where simulation work needs. Okay, so with this, I will end my presentation. If you have any doubts, then I am here to answer your doubts. Okay.
Dr. Mk Patil, sir, would you like to speak something?
Okay. Dr. PG Dikshit has given wonderful presentation. He started with the definition of simulation. First started with the definition of simulation and has given, simulation is a very burning topic because in every field of life, that is maybe concerned to IT industry, maybe concerned to artificial intelligence, or you may concern to any type of new things, or in research, if anything want to know new one, we use simulation. Professor Dikshit has given a wonderful idea how simulation calculated through integrals, mathematics, and testing of hypothesis, Monte Carlo simulation, and all other topics very nicely. So I thank Professor Dikshit for giving wonderful lecture in this session. Sir, anyone is to ask the questions? Professor Dikshit? Audience? Audience? Hello? Can you hear me?
Yes, sir.
Anyone asking the question? Participants from participant side? About simulation? Professor Dikshit is ready to answer.
Okay, anyway, my phone number is there with you. People can ask me if they have any difficulty, and this presentation is shared with you. You can, those who are interested, they can go through thoroughly and ask the questions later on also. Doesn't matter. Thank you very much for patient listening. Okay.
Thank you, sir.
Okay, thank you, one and all. Thank you, one and all. So
thank
nice
you. I'll close.
Okay, we'll close that.
I wholeheartedly thank Dr. Mk Patil for your valuable time with us, sir. Thank you. I also thank Dr. PG Dikshit for such a wonderful presentation. I once again thank you on behalf of PC Jabin Science College, Department of Statistics, and Organizing Committee. Thank you. Now, it's my immense pleasure to introduce Dr. VB Ghurte, Professor, Department of Statistics, Solapur University, Solapur. Dr. Vikas Bhaurao Ghurte has completed BSc, MSc, PhD in Statistics at Shivaji University, Kolhapur. Sir has teaching experience of 33 years and also has an impressive administrative experience. He has served as Registrar, Officiating Registrar, Director at Punyashloka Ahilya Devi Holkar, Solapur University, Solapur. So with this brief introduction, I welcome Dr. VB Ghurte. I welcome you, sir, and I request you to carry on with the session. Over to you, sir.
Okay. Now, good afternoon to everyone. Thank you for introduction.
Sir, you are not audible, sir. Either.
Yes, sir, you are audible.
Okay. First, I would like to thank Dr. Mk sir, convener, and also organizing committee of this national level conference for inviting me for chairing this session. I think it is a last session, and total 5 research scholars are going to present their research work in this session. All are expected to have 10 minutes Out of these 10, 8 minutes are for presentation and 2 minutes for discussion and queries. So first research scholar is Shubhashree Joshi from Department of Statistics, Bangalore University, Bangalore, and title of the paper is Entropy Estimation for Generalized Pareto Distribution. So I request her to start her presentation.
Okay, sir. Okay, sir. I'll start. Good afternoon, everyone. I'm Shubhashree Joshi. I would like to thank the organizers for giving me this opportunity to present my research work in this conference. I'm presenting a paper titled Entropy Estimation for Generalized Pareto Distribution. This is a joint work with Professor Parmeshwari Pandit sir. Plan of the presentation is as follows. I start with the introduction. Entropy estimation of generalized Pareto distribution is given, and the estimation is based on upper record values. Then simulation study is conducted, and then I conclude with some references. Entropy is a measure of expected value of information that contained in a random variable. Shannon 1948 introduced the concept of entropy as a measure of information. Then X be a random variable with cumulative distribution function f of x and probability density function f. Then the Shannon entropy is denoted by h of x, which is given by the following expression. Shannon entropy is applied in various areas like physics, statistics, economics, information technology, etc. Many researchers have addressed the problem of entropy in different cases, like in sensor data, in order data, and also estimation of entropy is considered using record values. Like Shao and others 2015 studied the Bayesian estimator of entropy for Weibull distribution based on generalized progressive hybrid sensor scheme. Hassan and Zach 2019 considered maximum likelihood estimator of Shannon entropy for inverse Weibull distribution under multiple sensor data. CO and others 2012 considered entropy estimation using upper record values for generalized half logistic distribution. Chakwa and Asha 2018 considered estimation of entropy for generalized exponential distribution using record values. Here Shannon entropy for generalized Pareto distribution is considered. This generalized Pareto distribution was introduced by Risa and others 2010 with the parameters as alpha and lambda, which has the following probability density function and cumulative distribution function. The Shannon entropy is obtained by the following expression. Now, the Shannon entropy of generalized Pareto distribution is a function of a parameters alpha and lambda. So here, estimation of the parameters is considered using upper record values. So the main idea of record values was introduced by Chandler in 1952. Then this record values has an application in various fields like sports, hydrology, and life tests. For example, a wooden beam breaks when sufficient perpendicular force is applied to it. Electronic component ceases to function in an environment of too high temperature, and a battery dies under a stress of time. So when the measurements may the measurements may be made sequentially, and also only the larger or a smaller values than all the previous ones are recorded. So the advantage of using these record values is when the measurements made is considerably smaller when compared to the complete sample size. upper record values can be defined as let xi be a sequence of independent and identically distributed random variables with a continuous cumulative distribution function and probability density function. An observation xj is called at the upper record if its value exceeds all the previous observations. So then xj is considered as an upper record. So analogous definition is the lower record. Here, the likelihood function for generalized Pareto distribution is considered and the log likelihood function is given, then the likelihood equations are obtained. So the closed form expression is difficult to obtain, hence the iterative technique is used. Here Newton-Raphson method is used. Then the maximum likelihood estimator of a Shannon entropy is obtained by the following expression. Simulation study is conducted for this parameter values for the illustration. Here, the true value of the Shannon entropy is given. Then it is observed from the tables that as the sample size increases, mean square error is decreasing, and the estimated value of the entropy measure is approaching the true value. And we can observe that more the entropy, it indicates that the sample has the lesser information. Here, we have derived the Shannon entropy measure for two-parameter generalized Pareto distribution. Then the Shannon entropy measure is estimated using maximum likelihood method based on upper record values. And it is observed that as the sample size increases, the mean square error is decreasing. Then the estimation of Shannon entropy using the Bayesian method is under progress. These are the references. Thank you. Thank you, sir.
Thanks, madam, for a nice presentation on entropy estimation. If anyone has a question from audience. Any questions or query regarding this presentation?
Sir, you can please go ahead.
Yes. Okay. Thank you, madam. Then we'll call next scholar, research scholar, Deepa Yogesh Kamath, Department of Statistics, Government Science College, Bangalore, and title of his presentation is Some Distribution Tree Tests for Spatial Two-Sample Location Problems. Deepa ma'am.
Yes. Good afternoon, everyone. Myself, Deepa Yogesh Kamath from Nrapatunga University, Bengaluru. Firstly, I would like to thank the organizers for giving me this chance for presenting my paper in this conference. And I also congratulate them for the wonderful conference. And I'm presenting the research paper on the topic, some distribution free tests for special two-sample location problem. And it's a joint work with Professor Parameshwar V. Pandit, and I'm also thankful for him for his encouragement for the research work. To start with, the plan of the talk is as follows. Start with introduction, then literature survey, proposed class of tests, asymptotic distribution of DPK, asymptotic relative efficiencies, then small sample power computations, and I conclude with the remarks and the conclusions and then references. So two-sample location problem, everyone knows that it's a very fundamental problem in statistical inference, especially in non-parametric inference. It has got a lot of applications like fields like economics, botany, medicine, psychology, and etc. a particular type of two sample location problem of comparing the performances of two packing machines in which one machine may underfill the packets and the other may overfill the packets on an average, and such particular problems can be studied under special two sample location problem. Here one wishes to test for point of symmetry versus an appropriate alternative. A number of distribution-free tests are available for two-sample location problem, namely Mann-Whitney's test, Moore's median test, Gastwit H&L test, normal scores test, RS test due to Hogg, Fisher, Randall's, Shetty and Govindarajulu, test due to Matheson, Shetty and Bhatt, test due to Ahmad, Zai and Pribe, then Stephenson and Ghosh, Bhatt and Patil, Kosler and Kumar. So many of them have studied and shown interest in comparing the two populations which differ only in location. Recently, Shetty and Umarani and Pandit and Acharya are available for the literature for special two sample location problem. So suppose if we have two independent random samples, x1 to xm and y1 to yn with the CDFs f1 of x and f2 of y, here the problem is to test the location parameter theta equals to 0 against theta greater than 0, and we are assuming here f of 0 is equals to 1 by 2. And the proposed class of test statistic to go for this is a U statistic, two sample U statistic. It is defined by dpk, and it is 1 over m2's p n2's k and h summation of h of x1 to xp y1 to yk. Here p and k are the subsamples sizes which are drawn from x and y samples without replacement from x and y samples. And h of x1 to xp, the symmetric kernel, we say it as a symmetric kernel, which is depending on the median of the x samples and minimum of the y samples. And p is taken as an odd integer and such that it lies between 1 to m and k is between 1 to n. And as I said, it is a two sample U statistic with the kernel of degree p comma k, and for testing we are taking large value of dpk is significant for testing the hypothesis. The asymptotic distribution of dpk, it is given by, the mean is given by 1 by 2 to the power of k plus 1 under h naught, and the exact variance of dpk is difficult to obtain, so we go for asymptotic variance of dpk by using the generalized use statistics theorem due to Lehman 1951. And the theorem says that if two independent random samples are from the CDFs f of x and g of y, x and y, then if we are considering h as a symmetric kernel of for an estimable parameter gamma of degree pk, then the root of n dpk minus expectation of dpk has a limiting normal distribution with mean 0 and variance p square zeta 10 by lambda plus k square zeta 01 by 1 minus lambda. Here lambda is nothing but the limiting sample, it's a limiting ratio of the sample size to the total, and it always lies between 0 and 1. So, and this variance should be positive, and capital N is m plus n, and whatever zeta 10 and zeta 01 are the covariance terms as like this. So under H naught, we have evaluated zeta 10. These are the computations of zeta 10. Computations include all these steps. And the expression 3.1.3 gives the expression for zeta 10, and zeta 01 is evaluated in this way. And this is the expression for zeta 01. And coming to the asymptotic relative efficiency, Pittman 1949, he defined asymptotic relative efficiency of one test relative to the other test Q as the limiting ratio of the sample sizes to obtain the same limiting power for the sequence of alternatives converging to null hypothesis. By Noether's theorems, it follows that ARE of P comma Q is efficacy of P divided by efficacy of Q the whole square, where efficacy of P is defined like this. And for the efficacy of the proposed test is given like this. And the main aim is for comparison purpose. We are considering here test due to Shetty and Umrani, 2005, U1 KK, U2 KK, and U3 PP, and Pandit and Acharya, WKP. The various values of AREs relative to this are given here for the different values of K and lambda. Here we have evaluated in this table, and here the value, suppose for the first value it is 0.6784 for k equal to 1 and lambda 0.1. It says that in this particular case, for the ARE of D3K relative to U1K means we need approximately 0.6784 times many observations for U1KK to achieve the same power. Okay, we need more observations for U1KK. So this is D3K relative to U1KK, then D3K relative to U2KK, then U3PP, and this is the area of D3K related to WKP. Here the values of P are for the first one P equal to 3 and the next P equal to 5, the bracket. So we have conducted a simulation study also. A simulation study is conducted to evaluate small sample performance by estimating the power of the test for DPK for different distributions like normal, Cauchy, logistic, and Laplace by generating 1 lakh samples of different sizes. And here we have compared that powers with the U1KK, U2KK, and U3PP. And in each case, we have drawn the power curves for different values of P and K. This is the power curve we can see for DPK, the blue color line we can see here. It is compared with U1KK, U2KK, and U3KK, different lines we can see. And it is for 5%, and the second one is for 1%. And we are observing that this is for normal distribution for different values of K and P. Previously, it was K equal to 2 and P equal to 3. Now it is K equal to 3, P equal to 3. Similarly, for Cauchy distribution also we have seen for different values of K and P. Logistic distribution. And then last one is Laplace. So coming to the conclusions, we have the proposed class of test DPK for testing H0 against H1 is consistent as expected value of DPK is greater than expected under H1 is greater than expected value of DPK under H0. And we are seeing that this is root n DPK minus expectation of DPK is asymptotically normal from Lehman 1951. And the performance of the class is evaluated in terms of AREs. And we have seen from tables that our test performs better in all the cases which are specified here. That is test due to Chetty and Umrani and Pandit and Acharya. And we have done small sample power. Small sample powers are also estimated using simulated data, and it is observed that power increases as the value of theta increases, and it is also observed that when we compare the powers, DPK is more in all the cases. So these are the references. Thank you.
Thank you, madam, for a nice presentation. If anyone has a question, they can ask. Any questions?
Sir, if they have any questions, they'll raise it in a chat box.
Okay. Next candidate is Dr. Prakash Chauhan. He is Head and Assistant Professor, Department of Statistics, Srimati Kasturbai Walchand College of Sangli. And topic of his presentation is applications of fuzzy ranking methods in replacement analysis. Dr. Chauhan, sir.
Prakash sir.
Hello.
Yes, sir. Yes, sir.
Deepa madam, please stop your presentation.
Hello, I am ready.
Okay, sir.
Just a minute. This is visible?
Yes. Yes, visible, sir.
Okay, thank you, sir. Myself, Prakash Chauhan, Department of Statistics, Srimati Kasturbai Walchand College, Sangli, Maharashtra. Title of my research paper is Application of Fuzzy.
Sir, please call the next candidate. Sir.
Okay. Next candidate is Satish Bhatt, Department of Statistics, Yuvaraja College, University of Mysore, and his title of presentation is An Alternative Method of Subset Selection.
Sir, looks like he has not joined the meeting, sir. Can you please go to next candidate?
Okay, next candidate, Dr. Sandesh Kurde, MES Anna Saheb Garware College, Pune. And topic of his presentation is optimization of stochastic demand and exponential deterioration type inventory model using evaluatory algorithm.
Okay, 1 minute, sir. I will share my screen. Hello, am I audible to all?
Yes, sir.
Okay, 1 minute. I will share my screen.
Sandesh sir, are you there?
Madam, yes, I am here.
Yes, sir, you
Please
are
1
audible.
minute. Please wait 1 minute. I will share my screen.
Okay.
Please allow me to unmute myself, madam. Please allow me.
Yes, sir. You're on unmute only, sir.
Okay, madam. Please.
Sir, can you please hurry up?
Madam, I am joining from the laptop, but it takes too much time. Yes. Now it is okay. I will share now. I will share my screen. Okay, now it is.
Prakash, are you ready now?
Okay, shall I share my screen? Hello.
Yes, sir, please. Sir, you can start with your presentation.
Hello all. Is my screen is visible to all?
Yes, sir. Yes, sir. You can go ahead. And your time limit is 8 minutes, sir. Sir, please go ahead. Sandesh, sir. Sir, you're on unmute only, sir. Please go ahead.
Sorry. Hello, am I audible?
Yes.
Sir, you are audible, sir. Please go ahead.
Okay, madam. Okay. Okay, so hello, myself, Sandesh Kurade. I'm from MES Abasaheb Garware College, Karve Road, Pune. I'm not sure. Okay, so my title of my presentation is Optimization of Stochastic Demand and Exponential Deterioration Type Inventory Model using Evolutionary Algorithm. This is the abstract of my presentation. Basically, supply chain is a set of interconnected facilities like suppliers, manufacturers, retailers, and customers. So at every node of supply chain, inventory is maintained and to satisfy to uncertain market demand of the perishable item. So this is the main goal of a supply chain. So in this paper, I have considered single stage supply chain, so which consists warehouses and retailers. So at the warehouses as well as retailers, at both the point, inventory is maintained to satisfy this market demand. So the basic goal is that to develop the economic order quantity inventory model by assuming selling price dependent market demand under exponential deterioration rate with linear time dependent holding cost. Also, for solving this inventory model, new optimization algorithm using genetic algorithm is developed. So, introduction. The analysis of inventory system with stock dependent demand rate has become an interesting topic in the field of inventory control. Basically, inventories are the physical stock of goods, and these are maintained such that the profit of the industry or the supply chain is maximum or the loss is minimum. It is always generally tendency that lower the price of a perishable item, higher the demand pattern. This is a review of literature. The first pricing inventory model were developed by Dye et al. In 2007, Abad in 1996 and 2001, and Chang et al. In 2006, in which they have developed economic order quantity inventory models with price-dependent demand. Das et al. Developed an inventory model with price-dependent demand under partial backlogging. The proposed model was solved using 3 different hybrid particle sum optimization. In 2009, Panda et al. Developed an inventory model under partial backlogging. These are the other related literature reviews. So from the above extensive survey, we get clear idea that price-dependent demand with holding cost as a continuous increasing function of time is not considered by the several authors. So this is the graphical representation of inventory system in complete backlogging. In this paper, while developing the inventory model, I have assumed that shortages are allowed there and they are completely backlogged. So from 0 to T1, this level of inventory is decreases due to satisfying the market demand as well as the deterioration of the perishable item. After the T1 to capital T, there is a demand from the market, but due to unavailability of inventory, there is a shortage period. These are the assumptions. The inventory level decreases from level S due to satisfying the market demand as well as deterioration. And during the period T1 to capital T, demand is completely backlogged. These are the assumptions. Replenishment is instantaneous with infinite rate and finite size. Lead time is negligible. System involves single perishable item. Rate of deterioration follows exponential distribution, and demand of the perishable item is dependent linearly on the selling price, where P is the selling price. This Ka is a demand scaling factor, and B is other parameter which affects to the selling price. Shortages are permitted and they are completely backlogged. The unit cost, holding cost, ordering cost, all are known and they are remain unchanged during the planning period. These are the notations where the main thing is there are 2 decision variables, capital T and T1, where capital T be the length of the inventory cycle and T1 the length of time after that shortages will start. And this is the profit function pi. So objective is that to maximize the profit function under these 2 decision variables. So behavior of the inventory level is represented by following linear differential equation. So 0 to T1, the level of inventory is represented by this differential equation, and T1 to T, there is a complete backlog period. So the level of inventory is represented by these differential equations, say equation 1 and 2. And at the boundary conditions, solutions of these 2 conditions is at 3 and 4. Now from equation number 3, we get the maximum inventory level, and which is given in equation number 5. So from this, we get economic order quantity, that is Q, in equation number 6. So profit function is nothing but per unit time is gross revenue minus total cost divided by T, where total cost consisting various cost components like deterioration cost, shortage cost, material cost, holding cost, and order cost. So deterioration cost is given in equation number 8, shortage cost in equation 9, Material cost is in equation number 10. Holding cost is in T11 and gross revenue is in equation number 12. This is the profit equation which represents the economic order quantity inventory level. So from this inventory level, I have obtained this profit expression for the single stage supply chain. So this is the optimization problem. Maximize this pi of T1T subject to T1 is less than or equals to capital T. So for solving, I have developed a new optimization algorithm using genetic algorithm, which consists 3 genetic operators: selection, crossover, and mutation. This is the algorithm. Now, for solving this equation number 14, the profit expression, I have used these parameter values: reproduction, that is tournament selection; crossover, 1 point crossover with crossover rate is 0.6; mutation, the beat-wise mutation with rate is 0.6, and so on. This is the numerical example. So for solving, I have considered, these are the parameters, all the cost values in dollars. So order cost, I have considered $500 per order, purchase cost $15 per unit, deterioration cost $9 per unit, shortage cost is $9 per unit, and this is the selling price per unit. So demand function is nothing but this, and these are alpha, beta, theta, the deterioration parameters, and the alpha, beta are the linear holding cost parameters. So the formulated model gives the optimal result using genetic algorithm is $869.89 with this economic order quantity. And this is the convergence plot for, I have considered variation in linear holding cost. So we can see that initially I have taken alpha is 10, alpha 20, alpha 40, and alpha is 50. So we can see that as alpha goes on increases, the optimum profit is go on decreases. So this is 860, 840, 800, and 760. So this holding cost is linearly affected on the profit. So this phenomena is not considered by the authors while developing the economic order quantity inventory models under the deterioration rates, various deterioration rates. So this is my contribution. So lastly, I have the conclusions. In this paper, an economic order quantity inventory model is developed under various realistic assumptions such as price sensitive market demand, exponential deterioration rate, linear time dependent holding cost. Shortages are allowed and they are completely backlogged. In future, the formulated model can be extended for multi-item inventory model with several price pegs, different deterioration rates like Gompert distribution, then gamma distribution with variable lead time, etc. These are the references I have used for develop this model. Thank you. If you have any questions, then please ask me.
Okay. Thank you, sir.
Thank you, sir,
for your nice presentation.
Yes, thank you, sir.
Is there Dr. Prakash Chauhan sir present? Chauhan sir?
Yes, sir. He is going to present now.
Okay. Okay.
Prakash, sir.
Hello, sir. Hello, ma'am.
Yes, sir. You are audible. Yes, sir. You can start with your presentation.
Okay, thank you. In this paper, already due to internet issue, my paper is just I present once again. Thank you for the coordinators, please giving me the chance. Topic of my paper is application of fuzzy ranking method on replacement analysis. In this paper, two fuzzy ranking methods are used and multiple criteria decision making is used for the replacement purpose. This method reduces the failure and high utilization of the component life. In this paper, a triangular membership function is used for the to choose the most efficient maintenance approach. Two methods, simple additive method and multiplicative exponential weighted methods are used. Lastly, the numerical example is taken to illustrate to verify effectiveness of the proposed methodology. Introduction. In the modern competitive and commercial climate, economic replacement of the component is very necessary, and we know that the replacement of the component is depend upon the proper maintenance time. When the proper maintenance is proper, it affects the replacement cost of that equipment is reduces. And conventionally, equipment maintenance analysis has been mostly done by a deterministic and crisp manner. The question of vagueness in maintenance is usually ignored. In this paper, I use the fuzzy multiple criteria decision making theory to provide the suitable tool for taking this ignored maintenance strategies. In this paper, I use the fuzzy multiple criteria decision evaluation methodology for selection of the most efficient maintenance approaches for the replacement purpose. And lastly, the typical example is taken. Maintenance approaches for the equipment. Mostly, I consider 6 maintenance approaches. Failure-based maintenance approaches. Second is the preventive maintenance approaches. Third is variance-based maintenance approaches, reliability-centered maintenance approaches, and total preventive maintenance and total quality maintenance. These are the various maintenance criteria considered for the proposed study. And next is a fuzzy multiple criteria decision making theory. In the fuzzy multiple criteria decision, it is the finite set of alternatives among which the decision maker can take and select the proper decisions of the maintenances according to their weights. In this paper, the simple additive method and the multiplicative weighted method is used. Here, triangular membership function is used for the calculation purpose. In equation one is the fuzzy triangular membership function. The same paper, linguistic variables are used. The theory of linguistic variable is used to express the vague values in the human cognition over the evaluation criteria. In the proposed methodology, the table number 1 shows the various maintenance approaches evaluating the failure causes. C1, C2, Cn are the criteria that in the given in the paper. These are the failure causes, and A1, A2, AM are the respective maintenance approaches. These are the alternatives. By using the first method, a simple additive weighted method, and second is the multiplicative exponential method. Directly, I go to the numerical example. I consider in the sugar mill industry, I take various criteria like linguistic variables are used, the possible ratings, and also I use the fuzzy rank variables. These are some linguistic assessments with respect to weights. In table 3, it shows that the linguistic assessments of cost and weight, the failure causes C1, C2, C6, and respective maintenance approaches are here with respect to weights W. directly go to the, after the calculation, this is a normalized weighted decision matrix, and using the utility function and the first method of simple additive weighted method, the ordering maintenance approaches are, the cost of the total quality maintenance is very high. It is greater than vibration based maintenance. It is the value of the greater than total preventive maintenance. It is greater than reliability centered maintenance. And the very low cost.
Hello. Hello. Hello.
Sir. Prakash sir.
Hello. Hello.
Sir, you're not audible, sir. Prakash sir.
Hello.
Okay, Dr. Ghute sir, there is another presentation here.
Okay.
Please let me announce, sir.
Yes, ma'am.
I request Dr. P.Y. Patil, Pitambar Patil, Associate Professor of Statistics, to present his paper. The title is Pool Maximum Violation Region Algorithm. Dr. Pitambar Patil, sir, please go ahead.
Okay, madam, thank you. I have shared my file directly. Word file is there. It might be visible for all of you.
Yes, sir.
Okay, thank you. Good evening to all of you. I'm here to present algorithm, pooled maximum violation region algorithm. It is myself and my research guide, Dr Mk Patil. He is retired. He was former professor and head Department of Statistics, University Kolhapur. Okay, so with this, let me go through abstract and just how many time I am here? I have just
8 minutes. 8 minutes.
8 minutes. Okay, so I will cover within that. So here abstract is this: we came across estimation of unknown probability density function. This unknown density function itself may have some known constraints, and hence it is trivial to expect the same constraints from its density estimator too. In this article, we consider density estimator is given or already estimated, but it may not satisfy required constraints. And here required constraint is non-increasingness property of that estimator. Hence, we provide an algorithm to obtain closest non-increasing function to a given density estimator, closest under these three norms: sup norm, L1 norm, and L2 norm. So here is the introduction. I have just given very brief introduction. So many times we came across estimation of density, and there are references, and out of that I have mentioned here. Finally, we'll get that seventh number is there. Though density is unknown, it may have some known restrictions on it, like symmetry. Means you might be knowing that density is unknown, but it is symmetric, or it has unimodality, or decreasing nature as its domain goes away from its modal value, etc. Means these are restrictions on that density. So such references are there, 1 to 5. So therefore, it is trivial expectation that such constraints should also satisfy our estimator too. So here we are considering decreasing or non-increasing nature of on a density estimator on its positive support upwards. We have modified it in such a way that it becomes non-increasing as well as closest to given density estimator. So first of all, I have density estimator, but constraint is that it should be that non-increasing nature on its positive support, and therefore if it is yes non-decreasing, it is well and good. So you have to stop there itself, and there is not necessary for modification in it. But the restriction is that it should be decreasing as it goes away from its modal value or on R plus. So in this case, we have proposed here algorithm called pooled maximum violation algorithm, and then obtain closest non-increasing function to a given density estimate closest under these three norms, and these are references for this. So initially there in Robertson, Wright and Dijkstra, he gives algorithm called pool adjacent violation algorithm, PAVA in brief. So they just modifying function in adjacent, but what we are doing here is we are modifying function on that its maximum violation region. So we'll look into that. So in general, here we are explaining algorithm. So function is r plus to r plus arbitrary function. We are assuming we are assuming that this is known, means that whatever estimate is there, it is known. And of course, it is on r plus to r plus, be arbitrary function. In the following, for notational convenience, we refer non-increasing property of a function as p, and v of f is equal to x such that fx is strictly increasing at x. A set on which f violates p, it is vf. And an interval uv is said to be violation interval if it does not satisfy that property p. And of course, an interval AB is said to be maximum violation interval of function if FB minus FA is greater than or equal to FB dash minus FA dash for any violation interval A dash B dash. So we have to modify function f on the on this interval, of course, not only A to B, but that violation region also we modify. And here such modified function we name it as f1. Okay, so by suitable constant L, of course, on that violation region we modify that function by a constant value L. And however, such constants at each stage of modification can be selected optimally under a specific norm distance function, and we consider the norms as sup norm, L1 norm and L2 norm. If does not violates P, then as I told you, no need to modify that function. So if f violates property P, then there exists at least one violation interval, and we assume these three conditions on that function f. It is finite, its integration is finite, and as if density without loss of generality, we expect that integration of that function is equal to 1, and that fx has finite number of turning points, means there is limitation, means points of local maxima and minima. So those are finite. So here is the algorithm we are developing. So first step is select a function, test given function for its violation property. As I've told you here, violation property is non-increasingness. If not that satisfies, then you say it violated. So, and of course, if no violation, stop there itself. Otherwise, go to step 3. And step 3 is how to modify that function. So how to modify is here AB is maximum violation interval for F. So of course, for L between A to B, we define A1L as infimum of x such that fx is less than or equal to L, and B1L is equal to supremum of x such that fx is greater than or equal to L. So here our AL, I have defined it as x such that A1L is less than or equal to x less than infinity, and fx is greater than or equal to L. And BL is defined as x such that x is above 0 but less than B1L, and fx is below L. Of course, we assumed it is positive, non-negative. So here define DL is equal to AL union BL, and that itself is A1L to B1L. So in the following, for notational convenience, we just ignore that L inside that, and we just name those as A1, B1, AB, and D respectively. Note here, A1 is less than A less than B less than B1. So we modified function as like this. On that violation interval, we have defined f1x is equal to L itself, and of course otherwise it is fx, it's as the given function. So this is my This is a modified function, f1x. Now, in the above, problem is how to find out that L. So, modified function D on the domain D, it is constant. And it is to be noted that f1x is greater than L for all x less than or equal to a1, and f1x is less than L for all x greater than or equal to b1. So typical function I have shown here in diagram, so that will be more clear for all of us. So it is a given function initially, this dot. Then we have to find out maximum violation interval here. Smallest value is here at A, here largest value for function is here. So A to B is maximum violation interval. Now what we do, you find out A1 and B1 such that below means you go on decreasing your x values up to A1 so that your function is yes, above L, and after B1 your function is below L. So now we are defining A1 to B1 as our set D on which we are modifying that function. And of course, these are L, BL. I have used those shades here. Okay, so we have to modify a function over this A1, B1. So how to modify? For that purpose, I have to run fast. Time is of course less. So step 4 is identification of two functions on disjoint intervals. So phi f1 is equal to phi, then means null set, then declare f1 is non-decreasing and stop. Else identify two functions below a1 and above b1 such that f11 is f1x and f12 is f1x for x greater than b1. And again do the same thing for this modified function f11 and f12. So in the above, choice of L is not unique. You can choose any L. But here we want to obtain it such that it is modified function is closest to the original one. So for that purpose, we have defined a distance function and distance between original f and modified function f1. So the closest function f1. Hello.
Sir, can you please conclude?
Okay. Yes, I have derived. We have derived these two lemmas, and what I have to say, and using those lemmas, we have obtained those L values. Just let me go to direct comments. Performance of that function, that algorithm is, even though there are at most k number of trading points, it may require less number of iterations because of modification of function on D, and it is superset for a to B interval. And of course, it is efficient than PAVA. And if your norm is L1 norm, then median value comes as L there, and if norm is L2, then arithmetic mean comes as L value. And these are key references. Okay, thank you then.
Thank you, Patil sir.
Thank you, sir. Thank you.
Nice presentation. I think all participants are over, and with permission, I declare that this session 4 of oral presentation is over. Once again, I thanks to organizers for giving me opportunity for chairing this session. Thank you. Thank you much, sir. Thank you all. Thank you.
Thank you, sir. Good day, sir. Thank you, sir.
On behalf of
PC Jabin Science College, Department of Statistics and Organizing Committee. I extend my gratitude to Dr. VB Ghute sir, and also would like to thank all the research scholars for their presentation. Thank you, sir.
क्या चल रहा है? हाँ? Kiran, continue matter.
Now, I request Dr. CM Mat sir, Head of Department of Statistics, to present vote of thanks.
Good evening, all. Thank you. In such a prayer that cannot be seen or touched, it must be felt by heart. I feel honored and privileged to get opportunity to propose a vote of thanks on this special occasion. I, on behalf of Department of Statistics and organizing committee members, convey deep regards and hearty thanks to our honorable board member of KL Societies, Sri Shankaranaji Ayamanolli sir. I am also thankful to our principal, Dr. LD Horkeri sir. I, on behalf of KL Society PC Jabin Sanskar Hubballi and the entire organizing committee members, and on my own behalf, extend a very hearty vote of thanks to all speakers and research scholars for gracing your important work and sharing with us your findings and opinions today. I would like to thank all the honorable delegates who blessed us with their presence. I am very much thankful to all advisory committee members. Especially, I am very thankful to the advisory committee members, Dr. Mk Patil, Dr. VB Ghute, Dr. Pushpanjali, Dr. Parameshwar Pandit, Dr. Sujata Ingansetti, Dr. Sujata Sharda Bhatt, Surekha Manoli, PG Dikshit, Dr. Y. Ronath Reddy, and Dr. S.B. Javli, even Dr. M.N. Magiri. Really, I am very thankful to all of you. With your support and encouragement, I conducted the seminar with successfully. And invited speakers also. Words are not enough to thank their constant guidance and support to shape the conference. My sincere thanks to Professor Parameshwar Pandit, Department of Statistics, Bangalore University, Bangalore, for his help and support at various stages. Today, my words are not enough to express the gratitudes to Dr. S.B. Manoli, Dr. Sharda Bhatt, Department of Statistics, KUD, who graced us with the kind words on behalf of the principal. I would like to thank our colleague, Dr. Jagdish Angadi, Department of Physics, and IQSC Coordinator, Rajesh Nair, for his constant help and guidance for this radiated source of energy within us. They supported in all possible manner and powerful manner to organize this conference. My special thanks to organizing committee members, especially Shithilingappa Kadkol, Santosh Gorpade, and the BVCA coordinator Varnekar sir, and our BSc students Inosh. I'm very thankful to this support for conducting this seminar with technical supports here. And the full day stayed with us for conducting the very smoothly this conference. I am very thankful to Ms. Kiran Gargi for conducting the MOC of this function. I may like to express our sincere thanks to students of the department for their participation in the conference. I am very much thankful to all our colleagues and non-teaching staff members who always stand by us and motivate us. I feel proud. Thank you for making this event a successful one. If time is money, then today. You have spent millions for us. Thanks to all of you for making this event successful. Once again, thanks all advisory committee members and organizing committee members within the campus and outside the campus. And once again, I am very much thankful to all the members, especially Sir Gute sir. Thank you, sir. Thank you all the members, sir. And in the future also, we are conducting the such a seminar. If you are supported with us, definitely I'll organize the more number of conference or the seminar in the future days, sir. Thank you. Thank you once again, all of you, sir.
Thank you, sir.
In the part in the seminar in this conference, please give your feedback immediately by today within 8 o'clock. After 8 o'clock, your feedback for will be closed. Please, once again. And those who are presented papers, they will get the certificate after Monday onwards. Only today immediately after filling this Google form, you will get the participation certificate immediately. The one thing. And one more thing is, those who are presented the paper, please send your full length paper today only. Please, I am requesting all the members. Now I am sharing the feedback link to you, your group. That's a WhatsApp group. Please go through the WhatsApp group only, sir. Okay. Thank you, sir. Thank you once again. Pute, sir. Thank you once again here. Thank you, sir. Deepa, thank you. Okay. Once again, I am requesting all the members here. Please switch on the videos. I'll take the group photos, please. Group photos. Switch on the videos, all of you, please. Put at the group photos.
I once again thank everyone for your valuable presence. Thank you.
P.Y. Patil. Dr. P.Y. Patil.
Yes, sir. Yes, sir.
Question. WhatsApp Patil. Hello, all the participants. Feedback link also shared within the chat box. Please go through the feedback link.
Yes, thank you, sir.
Okay. Hello, participant. After giving your feedback, you may exit from the group meeting. Thank you, sir.